and also leads to the formations of primary amines like dimethyl amines and ammonia. These chemical compounds produced during spoilage, they are collectively known as total volatile basic nitrogens, and this is considered as the spoilage indicators for determinations of freshness of fish. So in respect to fish being highly perishable, there are expensive techniques to evaluate the chemical, physicals, and biological aspects towards freshness of fish. So these conventional techniques, they are expensive, lengthy, and tedious to operate, and also leads to sample destruction. So we bring polyaniline as it is a unique polymer that changes conductivity and color with the change in pH. As a result, it can be used as a leach-free pH sensor for monitoring volatile amines produced by the fish during spoilage. So smartphones, they comes with a CMOS sensor which could act as a detector, but they are not designed for optical measuring instruments. So they are registered for polychromatic light. But by integrating optical components and external broadband light source, it could produce a monochromatic light, which the sensor can easily detect a particular wavelength and act as a particle optical measuring instrument. First, in the work.
Synthesis is okay. You go to your sensing part.
Okay, sir. So this is the characterizations, and we find that the polyanilines were synthesized. And this is the schematic diagrams of the proposed sensing system. Here we put an external LED light source. This light will, the incident light emitted from this LED will pass through a slit, and here we use a pinhole of 100 micrometer, and it passed through the level polyaniline film which we develop, and this film, the light transmitted from the films will be collimated with a lens. Here we use plano-convex lens, and the light, the collimated light will be passed through the gratings, and the gratings will diffract the lights, and the spectrums will be captured through the camera through the camera of the smartphone. This is the final setup of the sensing system. And for monitoring of fish, we prepared fish fillets in a sterile conditions and store in an airtight glass container, putting the polyaniline film inside the container, attaching in the cap. So, and store at room temperature. The polyaniline film was analyzed every 2 hours interval till 10 hours, and we captured the optical spectrums of the film using the developed smartphone sensing system. The spectral information from the digital image was obtained using a software called ImageJ. This is how the film is exposed to the fish, and the spectrum is taken with the help of a smartphone camera, and the data was extracted using ImageJ software, and this data is validated with the conventional techniques for fish determination. So before the experimental trials, we calibrated the wavelength using two laser diode of non-wavelength, so that to match the pixel positions of the camera sensor to wavelength of the spectrophotometer. And the sensor is calibrated with the standard ammonia solutions, and the calibration curve was obtained to evaluate the ammonia concentration of the non-sample. And this was further correlated by findings the TVV values and microbial counts of the fish samples. Here the results, with the help of software, the optical image spectrum was converted into intensity into pixel curve, and it is again calibrated. Here it shows the linear relationship between the pixels and corrected wavelength, and the maximum transmission was observed at 544 nanometer, 554 nanometer, and the LOD was found to be 0.002 molar. This is the spectrum obtained from the extracted data. The resulted spectrums follow the similar trends with the spectra obtained using visible spectrophotometer. And there is no color change of polyaniline film prior to 4 hours. And this was detected both in the spectra where the intensity reductions can be seen from 6 hours. The polyaniline level steadily changes its colors nearly after 6 hours, and this is correlated with the TVV value of the fish, where in the initial periods of the storage, that is 0 to 4 hours, the values of the TVV was 10 to 25 mg nitrogen per 100 grams, where it is in accordance with the European Union standards, where the acceptable limit of TVV of fresh fish is 25 to 30 mg nitrogen per 100 gram. And it also correlates with the microbial count of the fish. As the storage temperatures increase, the microbial counts of the fish increases. This is the summary of the work. The response time of the film was found to be within 1 to 5 minutes, and the LOD of the WF sensor was found to be 0.002 molar. And we demonstrate a pH sensitive polyaniline film with the smartphone based sensor so that where the change of the color of the polyaniline film can be observed through the rear camera of the smartphone. I want to thank LSRB DRDO. We are thankful for funding the project, and also Professor Pabitranath and Mr. Diganta, Department of Physics, Tezpur University, for the help and assisting for the design and development of the cradle. Thank you.
Good piece of work. Okay. Mr. Monica, Mrs. Monica, good piece of work. Can you explain, go to figure 4A and 4B?
Yes, sir.
Yes. Can you explain once again what is for 4A? You have got the response from your
smartphone. 4A smartphone sensing system, and 4B is the response from visible spectrophotometer, standard spectrophotometers that we have used for analysis. So here,
have you tested your polyaniline film? Okay. Outside, other than fish, suppose you keep it in a solution and change its pH, whether it changes color.
Yes, sir. I have taken the standard as ammonia solution. So we take a standard as ammonia solution as a standard, and we have checked the response of polyaniline film in ammonia solution.
What is the response time to change the color?
So the change in color, the response times was between 1 to 5 minutes. The response, the change in color can be shown and within 1 to 5 minutes.
All the best. Good piece of work. All the best.
Yeah. Thank you so much, sir.
Okay, I have a question for you.
Yes, sir.
Regarding the slide you were showing earlier, the figure 4 and 5. Now, why do you think the variation in the second picture, that is using the standard spectrometer, in the higher wavelength region, it is not completely following what is on the left, isn't it?
Yes, sir.
Why do you think that is?
Yes, sir. This is the problems we are facing. Like, it may be due to the inbuilt filter present in the camera of the smartphone. So we are trying to extract the raw data so that we can come to an accurate reading.
So I want to say that if you're taken instead of this, if you're taken photographs, I mean you're taken photographs of the same events,
yes,
what
sir.
would it look like? Will it be closer to the smartphone image, or will it be closer to the standard spectrometer response?
So I didn't understand photographs of.
See, you photographic film if you use, okay. There's a sensitivity range for photographic film, and it is not linear. So, since if you are in my generation, you will go and photograph these pictures rather than photograph using a camera, not use a smartphone. So then the response, the log curve will not be a linear curve, isn't it?
Okay, sir.
So that is something which you should probably try, you know.
Okay, sir, I'll look into it.
I think the spectrophotometer is closer to the what the camera will take. Okay?
Okay, sir, I'll do it. Thank you so much, sir, for your suggestion.
Thank you, Monica. You can now sign off your presentation.
Okay, thank you so much.
So the next speaker is OP9, Jayanta Kumar Bharat. Whether he is available for the talk?
Actually, the speaker is not available, ma'am.
Yeah, then we will go to the next oral presentation. That is OP number 10, Ms. Arya Ajib. Arya Ajib, are you there?
Yes, ma'am.
Yeah, please share your screen. Try to please stick on to the timing. If it is beyond 7 minutes or 8 minutes, we will be stopping your presentation. Okay.
Excuse me. This is Dr. Shivadas. When is my presentation?
Yours will be after one more is there after that. Okay.
Okay.
Hope the screen is visible.
Yes, Arya, a little bit louder.
Okay, yes, sir. So, good afternoon, everyone. I'm Arya Ajib. I'm currently pursuing my MTech in Polymer Technology. And my topic for today's presentation is a wearable strain sensor for human-machine intelligence sensing. So this intelligence or interactions can be of different types. That can be human-to-human interaction, that can be machine-to-machine interaction, and that can be also where the humans interacting with or through the machines. That is the human-machine interaction. And this human-machine interaction itself can be of different types. That can be based on the image processing, that can be based on the IR radiation, and it can be based on the electromechanical signal itself. So my research area is mainly based on this particular electromechanical signal based one. So here what's happening is that there will be some sensor probe that get attached to the different parts of the body, and that will sense various human body action. And commercially, there are different types of sensors are available. But the problem with that is that they are having high cost. In here, you can see that it's IR camera based one and a touch sensor is available. So in this current scenario, what is our aim is to develop a strain sensor within low cost. While taking the cost as a consideration, we take the filler as a carbon black, which is a cheap filler. And actually, we did our work by inspiring from the nature itself. We know that in our human skin, whenever there is joints, there will be wrinkle. And it is that wrinkles that makes the movement of the joints easier. So we thought in that direction that while selecting a substrate that having the same particular phenomena, it will be easily used as a wearable sensor. So we used our substrate as the latex rubber band. The latex rubber band that comes under the class 6 biocompatible material that we can easily mount on or near to the skin. But the problem is that this rubber is insulating in nature. So to convert that into conducting, we just infuse our rubber with some conducting ink and we fabricated it. And also I told, hello?
Start. Continue.
Okay. So this latex rubber actually highly elastic in nature. So when we are stretching or bending it, there will be some cracks form. And actually we monitor our actions via the cracks form. And these cracks are generally reproducible in nature. So to prove that concept, we carried out some images. Okay. So here, the first one you can see that when it is at 0% strain, all the carbon particles will be in a very close proximity and hence the conductivity will be very high. But when we are stretching the rubber, okay, to say 100%, what happens is that there will be some micro cracks will develop. That micro cracks will impute the conducting path and the resistance will go higher. And upon further increasing the strain percentage to 200%, the cracks will be even higher and the resistance will be go higher. But the good part is that upon releasing, it's going back to the initial itself. And to prove the sensitivity of our sensor, we used our sensor at the different body parts, ranging from the low strain areas like the finger bending to somewhat higher strain, that is the elbow and the wrist, to somewhat higher strain than that the knee and all. And also, apart from this, we also used our sensor at the backside of the neck to find out the neck posture analysis. For any sensor, the stability is the much important factor. So to find out or to prove the stability of our sensor, we carried out 1,000 cycles of the bending angles. And we are gratified to observe a very good result upon this 1,000 cycle. So also for any wearable sensors, there are chances that may come in contact with the sweat and all. So the sweat stability is important factor. So to prove the stability of our sensor with the sweat, we carried out this artificial sweat stability, and we got a very good result. And apart from the voluntary measurements and all, we also applied our sensor for the involuntary measurements like pulse measurement and voice recognition and all, that having the strain range of less than 3%. And we not only restricted our application of the sensor to this also, we somewhat go to some practical level of application. That is, we used our sensor for a gesture communication device. So these all newspaper reports are focusing into one thing, that is the miscommunication between the soldiers in a group has risked many lives. So the only possible solution is that we need a smaller, lighter electronic device that will convert the gestures into command within no time. So what we done is that we used our sensor as a non-verbal communication device for the army. So for that, we need to place our sensor at the different joints of the hand, different parts of the hand itself. And when the soldier is bending or doing any action, there will be the strain change will be there. And that strain change is measured by the hardware and software, and that will convert the gestures into command. And we successfully carried out the 4 commands like rifle, dog, shotgun, and pistol. And moving on to the conclusion part, we developed a sensor that's cost-effective and user-friendly. It's flexible, stretchable, sensitive, and durable in nature. And moreover, we got an extensibility up to 250%. And the most prettiest part is that we got a gauge factor of 1.2 into 10 raised to 4. And none of the carbon-based strain sensor has got this much of gauge factor within this extensibility limit. And also, we got a long-term stability for 1,000 cycle and an outstanding stability for artificial sweat. And we hope in future our sensor can be used in interactive electronics, smart robotics, and healthcare application. And this all are my references. And thank you so much for a wonderful opportunity. Thank you.
Good piece of work, Arya. Can you go to that rubber being stretched and you have some crack patterns in that?
Yes, sir. Is it, sir?
Okay. Now you said that this is, see, when you are developing a crack in the band, you are essentially interfering with the conductivity of this material, isn't it?
Yes.
Carbon.
Yes, sir. Yeah.
But I think sweat also is a good electrolyte. It has sodium, potassium.
Actually,
so why do you say that it is stable in your readings are stable under sweat conditions?
Yeah. Actually, when we look
I'm
into the
graph, surprised about it.
Actually, when we look into the artificial sweat stability graph here, we can see that the resistance is actually decreasing. But it's like from 182 kilo ohms to it's going to 165. That is, the conductivity is increasing. But within that little range only. That's what we focused on. Okay.
So I think what is meant by artificial sweat?
Artificial sweat means we made the sweat artificially, not like we made with some electrolyte and all. That's what we do.
I think you have to fine tune your sweat stability studies a little bit more to ensure that the sweat conductivity due to the ions present in the sweat doesn't interfere with your normal readings. Okay.
Okay, sir. Yes, sir. Sure, sir.
Good luck. Good luck. All the best.
Thank you so much, sir.
Yeah, I have a question for you.
Yes, sir.
When you finally convert this into a device which the army or some soldiers will use,
yes, sir.
What are the chances of what the soldier intends to say and what is conveyed through the signals, which is now you're replacing the human factor by a machine, isn't it? Ultimately.
Yes,
so what are the chances of things going wrong? Where the soldier wants to stop some action, instead the signal says go ahead.
Okay, so for this particular device, we can set an on and off system, like just like our mobile phones itself. So if we want to convert any gestures or if we want to communicate, we can on that and we can do the like the commands and all. Then after that we can off that, like the system we can implement.
Is it possible for a human interface where the machine will say do something, but the person behind the machine can say, no, that is not what I want. You know what I'm trying to say?
I understand.
A human intervention, is it possible in your system?
Actually,
or it is fully automatic, fully
no.
given to the machine?
Actually, we are initially measuring the voltages, okay, corresponding to the. So
but
that
if the voltages, measured voltages tells you something, but the human behind the machine, the human sitting there, his intelligence situation of the military operation tells him, no, this is not what should be done. That means he wants to stop something.
Okay.
Is it possible?
For a particular command, there will be a particular voltage range.
Correct.
So it will come in that range only, it will sense.
Yeah.
So it's like that, sir.
So you think this will be a boon or a bane tomorrow?
Yeah, like the human machine intelligence will be good, sir. Like apart from replacing everything with the machine, the human machine intelligence will be good.
Can you do away with the human?
What, sir?
Can you do away with the human being?
No, sir, definitely
no. Okay. Thank you.
Thank you, sir.
Thank you, Arya.
Yeah.
So next is, I think next oral presentation is OP11. It's Anaga Baby. Anaga Baby, are you there?
Yes, ma'am.
Yeah, so please stick on to your timing. Please finish your talk within 7 to 8 minutes. Okay.
Yes, start, Anaka.
Good afternoon. So today I am here to present the topic textured NBT-BT lead-free piezoelectric ceramics for knock sensor applications. So let's start with piezoelectric materials. Piezoelectric materials are one among the smart materials which can convert the mechanical to electrical energy, which is used in the sensor applications, as well as electrical to mechanical energy, which is used in the actuator applications. There are a wide variety of sensors used in the various fields, but here we are mainly focusing on piezoelectric knock sensors. The piezoelectric knock sensors are the vibration sensors, which is used to detect the structure-borne acoustic oscillations in the automotive engines. A high-frequency vibration give rise to the sounds in the engines of automobiles, which is called knocking. And this knocking generally arises due to the low-quality fuels and the deposit on the cylinder wall. So, in order to avoid this knocking, a piezoelectric knock sensors are generally attached to the engine block of automobiles. So, when knocking occurs, due to the high pressure and vibrations, an electrical charge will be accumulating inside this piezoelectric ring element, which have the contact disc on both sides, through which the developed charge can be flown to the engine control module, which is called ECM. So, when ECM receives this electrical signal from the knock sensor, it can adjust the engine parameters and it retards the ignition timing until knocking stops. So these are the advantages of using knock sensor is it reduces the tendency of knocking, improves the engine performance, improves the fuel economy, secures the engine components, reduces the emission of the unburned gases. This is the main theory of knock sensors. So for every sensor, piezoelectric sensor, there will be one figure of merit. So knock sensors usually generally operate in the non-resonance mode with operating temperature from -40 to 180 degrees Celsius. So the major figure of merit for the knock sensor is D.G, where D is the piezoelectric charge constant and G is the piezoelectric voltage constant. Commercially, the piezoelectric-based compositions are generally used, which have the form figure of merit between 9 to 12 picometer cube per joule. Even though this piezoelectric material possesses excellent properties, the hazardous lead poses various threat to the environment issues. So we have to develop a lead-free based piezoelectric sensor for the daily use. Among these lead-free materials, the NBT-BT solid solution have been thoroughly investigated as a potential competitor for the piezoelectric based sensors. But in case of lead-free system, the piezoelectric properties are not that comparable to that of the piezoelectric. So the major technique we are introducing here is texturing. So in order to improve the piezoelectric properties, lead-free composition, which is along with that of the texturing is used in order to bring the D dot G value, that is the figure of merit, close to that of the PCT, which can be used for that of the NOx sensor applications. So as we said, the major technique we are using here is the texturing. Now, for the texturing, we require a template particle. This is the crucial step in the texturing, because in texturing, the ceramic matrix particle, that is here we are using the NBT based compositions, it will undergo the grain growth around this template sheet, and these particles will orient in the same polarizing direction as that of the template. So the synthesis of the template is the major step which has to be taken care in case of texturing. Usually the BT template is synthesized through the method called molten salt synthesis through the process called Topochemical microcrystal conversion method. This mainly follows two steps. Initially, the bismuth oxide will combine with the titanium oxide to give rise to Bi4Ki3O12, which is also called a bit. This bit, it has pseudoperovskite layer which is enclosed between the BiO2 layers. So this network between these perovskite slabs are generally weak covalent bonds. So in high temperature, in excess presence of barium carbonate, this BiO2 layer will be broken, and the barium carbonate Ba3 plus from this excess barium carbonate will enter into the structure and replaces the bismuth. So without changing any morphology or structure, the barium replaces the bismuth in bit to form the barium titanate. The following shows the XRD as well as SEM images of this bit. In case of bit, according to the standard JCPDS file, all the diffraction peaks are assigned to that of the bit. And from the SEM images, we can see that the bit usually have plate-like shape, and its size average length varies from 14 to 20 micrometer, and thickness is less than 2 micrometer. And we can see the XRD of BT templates. So when we are analyzing the XRD, we can see that this BT has a highly preferred orientation along 001 direction. Also, the splitting of this 002 peak around the angle of 45 degree indicates that the BT has a tetragonal structure in the room temperature. So, in order to quantify the degree of texturing, we are introduced. There is a factor called lodgering factor, which is measured by comparing the intensity of this desired peak to the total quantity of this peak. Lodgering factor is generally given as F is equal to P minus P0 by 1 minus P0, where P is calculated for textured and P0 for random. So I have already said that after the synthesis of this template, we have to create the matrix powder. So generally, the material of our choice is 0.93 NBT, 0.07 BT. Because we choose this composition because there is an NPB in this composition range. We know that NBT have a tetragonal rhombohedral structure in room temperature, and BT have tetragonal structure. So in 0.93 NBT and 0.07 BT, there will be an MPB. That is, there is a coexistence of the spaces, and there will be enhanced properties in that region. So we are preparing the NBT as well as BT, random BT through the solid state synthesis, which is followed like stoichiometric weighing of these raw materials, which is followed by mixing, milling, and then calcination to form the perovskite structure. Then XRD is taken, so we have obtained the single phase without any secondary phases. After this, after the synthesis of the both NBT and random BT, we have gone through the texturing. So in order to study the impact of this texturing, we have done texturing using random BT powder as well as template BT powder. So then we have tape casted, followed by the steps such as sintering to obtain the random NBT as well as textured BT. So the template particle we have chosen here is BT for NBT compositions. The template particle should satisfy the similar structure and less than 50% lattice mismatch between the template as well as matrix, high aspect ratio, and it should be thermodynamically stable within the environment. Next step is what is taken place in the texturing. We can see that here the matrix we use is NBT composition as well as template is BT. So during this texturing, the NBT compositions will undergo nucleation and grain growth in the same direction as that of the BT, and all these particles will be aligned in the same polarizing direction as that of the BT. So overall, there will be an alignment of these particles, and hence the properties will be enhanced through the texturing. So when we see this XRD of this textured ceramics, we can say that in case of random texturing, there is no preferred orientation. But in case of textured compositions, there will be very preferred orientation along 001 direction. Also, we can say that if you are increasing the soaking time, that is the soaking time of BT template in NBT metrics, we can say that the for soaking time for 10 hours, the lodgering factor reaches up to 92% of the 92%. And the figure shows the same images. So in the first figure, we can say that we can distinguish between the template and the matrix particles. Here, we can see the template particles which have the plate-like shapes, and the matrix particle is having the grain growth around this BT template. And next shows the backscattered image, which shows the perfect diffusion of these template particles into the ceramic matrix. And next section, we have given the cross section of this BT template. There is elongated grain growth. And last, we have given the barium mapping, which shows the chemical homogeneity of the compositions. So these are the achievements. We can say that after centering, we have polled the compositions and analyzed the D33 values. So we have seen that for NBT BT texture using BT templates, the D33 values reached up to 272 picocoulomb per Newton, and for random it is only 180. So by calculating the D.G value, which is the main figure of merit for the NOx sensor applications, for NBT BT texture, it reaches up to 8.4, which is close to that of the P30 used in NOx sensor applications. So from this, we can conclude that the textured lead-free 0.93 NBT 07 BT can be used as a very promising candidate for the NOx sensor applications. Thank you to my team members and the funding agencies, sir. Thank you.
Very good piece of work, Anaga. Can you go to slide number 3? Please go to slide number 3. You have come out of your presentation. Can you tell me why textured material show high value of D33?
Actually,
yes, why textured material show high value of D33?
In case of single crystal, there is only one alignment. There is no grain boundary. So all the properties is along the same direction. So there will be enhanced properties. But in case of random crystals, all the grains will be in random orientation. So there will be cancelling out the piezoelectric effect. But in case of texturing, if you are doing, we are aligning all these particles in the same direction of this BT template, the template we are using. So there will be overall alignment of these particles, and we can enhance the properties. So there will be no cancelling out of this piezoelectric effect due to random arrangement.
No, my question, you are talking about texturing, alignment.
Yes.
I am asking what is the reason for the increase in the value? Okay, please look at it. Okay, what is the reason for increase in the D33 value when all your domains are oriented in one particular direction? Okay, you just look at it and then we will get a better answer for that. Okay, wish you all the best. Next adjudicator, please. You understood my question, Anaga? Hello.
Anaga?
Yes, sir.
This, you just answer to what Kumar sir is asking. Whether you have understood this question.
No? You have understood my question, no? Just try to find answer. Why, when you are texturing it, the values are improving. Okay. Okay, Murali sir, please. I don't know whether he is around. Or can we go to the next presentation then?
Yeah, Anaga, thank you very much. You can sign off from the presentation now. Anaga, you please sign off.
Please exit. Okay.
So the next oral presentation is OP12 by Dr. T.K. Shivadas. I request Shivadas to kindly keep the timing of oral talks at 8 minutes itself. Over to you.
Yeah, please start, sir. Mr. Shivadas.
Hello.
Hello.
Ah.
Yes, sir, you may please start your presentation.
Hello. See, my work is on development of new sensors and techniques for applications in different sciences, applied sciences, including agriculture, etc. Total sensors. This development of sensors and new applications resulting in implementation as large national projects belong to ICAR, CSCR, DRDO, DOES, IITs, NITs, ONGs, GSA, etc. And they have been implemented. General information, fully indigenous technology, more than 150 sensors with location-specific operational features, implemented in more than 600 R&D institutes belong to ICR, CSR, etc., became part of 5 numbers PG, 5 numbers educational systems in 5 department universities under different areas in KUVOS, KUSAT, KACCR, SNOM, Indian Navy, Fisheries University, Mumbai. Technology initiated in ICR CAFT and expanded to more areas after commercialization through NRDC of India. It is very important to know how sensors with associated accessories developed indigenously have been implemented in different prime areas of the country, leading to Make in India vision of the country. Total sensors developed and implemented by others belonged to wide application areas: agricultural, ocean sciences, environmental sciences, safety, dam safety and its hydrometeorological environment, architectural structural engineering, hydrodynamic model engineering studies, investigations, model engineering investigations, fishing technology, post-harvest technology, coast and harbor engineering, soil and water conservation engineering, energy and environment, behavior studies of marine animals, etc. A few samples cases. See the total list of sensors developed indigenously and implemented in more than 600 R&D institutes, analyzing nature for analyzing natural processes and their just full exploitation of natural resources. How they could be incorporated in 5 numbers PG level education. Implementation of sensors and technology in more than 600 R&D institutions for analyzing different aspects of nature. So these are for solar radiation measurement. These are some 3 different type of sensors. One is for incident total reflection, incident and reflected. Second is diffused with omnidirectional property. That is radiation coming in all directions, PR value. Different designs with specific features can enable to conduct many novel investigations. Sensors and instruments were calibrated with available facilities in CWPRS, Pune, IMD, Pune's FCRA, NPL, IITM, etc. Others were self-calibrated and tested with suitably developed simulation facilities. This is a case of automatic weather station showing how different designs can be made, already implemented in many places, added with energy integration process, and also you can see that many added facilities are there for sensors of different types, from not only from the meteorological side, but also from soil, water, etc., resulting in different designs of areas and many places added. Research and development works carried out include new sensors, more than 150 numbers. We will get the details in annex array. New data processing facilities, new applications for better understanding of theory and basics of structural agricultural systems, new multidisciplinary data acquisition systems for direct measurements from open environment, large experiments in nature conducted for location-specific investigations. Nature of technology presented here is fully indigenous, already implemented in 600 institutions. Meteorological and observation, new sensors with uniform outputs, making easy standardization and physical processing. Additional hardware for detailed analysis and estimations as energy integration processor in order to make automatic estimation of the long-term effect of energy parameters. So this is a rain gauge. It has got its own additional features that it gives rain gauge with many added facilities and facilities including rainfall intensity for every 5 minutes. This is a graph prepared by that accordingly. This is a case of intensity for every 5 minutes. Graphical presentation of rainfall and the barographic presentation of intensity. So these are all some portable type of sensors for agricultural or agrometeorology, etc. Portable design with wind directionality and RHA and solar radiation. Direct. So this is a solar radiation based sensor for continuous measurements and continuously exposed to environment. So RH and temperature, X-ray, XRB, automatic weather stations are available with different sensors and their combinations to meet specific needs. List of different models available in XRC. So automatic weather station of installed in Kerala Agriculture University, micrometeorological investigation, smart sensors, fast response, uniform serial outputs to meet the fast changes inside plant canopy. Facility for energy integration also. This is a wind and wind direction sensor, compact and so operation at the solar on solar power. This is a sensor installed in Calcutta. For micromet studies at 2 layers. This is a very compact sensor to be inserted inside plant canopies and pick up fast change in signals occurring in small area. So another one portable type sensor designed for microclimatological studies. This is a part of a display system of the sensor in Agricultural University. Agroclimatological investigation with sensors developed for leaf temperature, leaf thickness, RHA, solar radiation, soil moisture, soil temperature, evaporation attached with the extra processes for energy integration process, disease forecasting units, etc. This is a case of weather stations, 19 numbers, 19 plus 1 number, instead of Mangambu station of Kerala Agricultural University. Came to Mangambu for 20 numbers weather stations implemented for specific investigations in paddy culture. Greenhouses investigations with the sensors with the wind velocity having diffused CO2 sensor for novel investigations, global warming studies in agricultural sciences. So this is a case of automatic temperature humidity chamber. Experimental setup designed for DNAU, KAU, etc. For micrometeorological studies inside the greenhouse. This is a case.
Sir, your time is going to be end.
Okay, I am just finishing. These are different sensors for temperature itself, but designed for different applications. I am giving details in annexes. Those who are interested can contact me. Sensors for solar energy. So, moving it. I am coming back. Finally, I am coming. So, some applications already made it throughout the country using that different type of sensors. Okay, I am just leaving. We can.
Sir, thank you very much. Sir, thank you very much for enlightening us with the various kind of sensors that have been deployed in various sectors like agriculture, fish, fisheries, ocean and fisheries, etc. Thank you very much for your presentation, and please accept our congratulations. Thank you very much. We will go to the next speaker.
Thank you, sir. So you can sign off now. എന്നാൽ ഞാൻ മിലന്തിനെ വിളിക്കാം.
Okay.
New presentation, sir.
Now there is no presentation. Dr. Shivadas, please sign off. Okay.
Yeah,
so with this, our oral section is over. Oral presentation is, sessions are over.
Okay.
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 So thank you.
Okay,
Thank you.
So we will continue with the next session, 8th session. This is the invited talks from 4 different dignitaries. So we will be starting this around 3 o'clock. That is 15 hours.
3 minutes. Okay.
So Murali sir, I think we can have a look at some of the shortlisted posters and come to a decision. So can I request Dr. Karthik to help us out in that?
Shall we do it here?
Sir.
Yeah.
We'll bring to your cabin, sir.
Okay.
Okay, sir.
So we'll meet in.
Sir, Kumar's cabin.
We'll meet in Kumar's cabin. Okay.
Okay, sir.
I'll go have some tea and then reach his
yes,
cabin.
sir. Thank you. Sir.
Okay.
Yeah, around 3:30 is okay. Karthik.
Sure.
Okay.
Okay, sir. Fine.
Dr. Karthik,
sir, kindly bring your list. Okay.
Yes, sir. Definitely.
The announcement from the chairman.
Dr. Karthik, I mean the same link will work, or should we go?
Yeah, same link, sir. Because the session is continuing.
Okay,
so the same link will work. Yes.
That's really good. Thank you.
Till the concluding session, it's still the same link.
Good.
Okay, good. Okay,
yeah.
good.
Hello, sir.
Hello.
Yeah.
Good afternoon, everyone. I think Professor Bonax has joined. Seema, madam, shall we start the session?
Yes. We can start the session.
Yes, ma'am. Professor.
So good evening to all. So we will continue with our session 8. So this session 8, the first talk is from Professor Bonax. Dr. Bonax is Professor Extraordinary of Physics, Schwein University of Technology, Pretoria, South Africa. Hello, all others can please mute their mic.
There was some echo in your.
Yes, Rija. Yes,
Yeah.
I'm in a conference.
Hello.
Yes, I'm in a conference. Yeah, I'll share this thing now.
So his current position is Chief Researcher at the DST CSIR Center of Nanostructured and Advanced Materials, Pretoria, South Africa. He did his postdoctoral fellowship at the CSIR's National Laser Center in 2010, and then started his career at CSIR DST National Center for Nanostructured Materials. He has so far published more than 100 papers in referred journals and more than 100 conferences and conference proceedings, 5 granted patents and 4 pending patents, and 1 product that is on diabetes breath analyzing glucometer transferred to industry. And he has guided more than 9 PhD students and a number of postdoctoral fellows and interns. He has received a number of awards, including the Excellence in Innovation Award received at the Future Education Summit 28 in Johannesburg, South Africa. It's my proud privilege to welcome you, sir. Professor Bonax, please.
Let me. Did I mute myself? Let me see. I think. Hello.
Hello. Sir, you may please share your screen, sir.
Am I audible there?
Yes, you are audible.
Okay. Good morning. Is it morning in India or?
It's evening, sir. It's evening, 3 o'clock.
Really? Oh,
Yeah.
I'm sorry. We are, I think, 3 hours behind you, yeah?
Yes, we are here. It is 15 hours. That is 3 p.m.
Okay. So then I should be very quick. I won't drag the conference. I don't know where to upload my.
You can share the screen, sir. You can share the screen. There is a button, share screen.
Yeah, let me see. Where is share? Share meeting information. We are used to Microsoft Teams now.
This is Zoom platform, sir.
Yeah, I can see.
Bottom, you can see start video participants. Yeah, share the screen.
I've got it. Okay. Share. Are you seeing my screen now?
Yes, we
yes.
Your screen. Please put it in PowerPoint mode, sir. Slideshow mode.
Slideshow, yes. F5, I think. Is it F5? Sorry. Presentation, slideshow.
Third one.
Okay.
One custom slideshow.
So from beginning, sir, you may just go to the right, left. Yes, sir. It's in slideshow now.
Like this, eh?
Yes. You can continue with your talk. You can start your talk, please, sir.
Good. Good morning, professors and doctors. My name is Bonex Mwakikunga. It's a large, such as a long surname. Of course, my main job is at the Center for Nanostructured and Advanced Materials, they call it CINAM, which is in CSIR. And then I'm also Professor Extraordinary at the Physics Department of the Tswane University of Technology. I'll talk about a product that we have just produced. It has taken us a few years since like 2013 or so up to today. But of course, apart from that, we've also been, why it has taken so long, because we are not like industry per se. We sit in between industry and the university. So we also do what a normal professor at the university would do, graduating students, publishing papers. So product development is just one of the things that we do. So it's that's why it has taken so long. Okay, so I'll just basically look at why we're doing this research and some impacts now, and how we have tried to commercialize this product, and where do we get the funding. Okay, so it's, I think you've seen this, I just Googled this from the internet. You'll see that the sensors are at the hub of many things: robotics, Internet of Things, you call it machine learning, and all this for IIR depends on sensors. And for us, we are working with nanostructured sensors, very tiny particles that would be probably lower than 20 nanometers. And we see quite enhancement in both sensitivity and also the problems that we encounter are that when they become very small, they now sense everything. So we have to now check what kind of things should we do to make the sensors very selective. So you'll see from this wheel, we are targeting mostly CO2 sensors. There's a colleague of mine who does CO2 sensors for especially food spoilage. And we also sometimes do flow sensors, because the breath analyzer needs to have flow meters and things to see how much of the breath has come in and how much we must expel and how much we must keep for us to detect. So we also use humidity sensors on your left here, because breath is very humid. So we need to know exactly how our sensors will behave in the humid conditions. And also we do temperature sensors on the right. So there's not much of other things that are on this wheel, like magnetic, we don't do ultrasound. No, these we leave to other groups to do within CSIR. Now, why did we have to do this research? Basically, there are two products, but I'm going to talk of only one product in this conference. And the first product is about a diabetes glucometer using breath. You know very well that the diabetes has been studied using breath for almost 30 years now, but we have very little success in this area. And in our group, we just found out why the world has failed grossly to produce a diabetes breath analyzer on the market. But it's a very big, lucrative business. It's sitting at currently $14 billion per year that the industry makes. Just those pricking devices that you see on the market, they are making a very good amount of money, $14 billion per year. So if you want to go into this area, you can, even if you take 10% of the market, you are, I think, talking of $1.4 billion every year in your company if you have to go into this one. So, but then the breathalyzer for diabetes in CSR has been, is no longer in our hands. We have, as researchers, we've done what we did. Now CSR are trying to work out how they're going to commercialize. In fact, they already have a partner, a company that will take over. They have signed term sheets and things. So this is why for research, I'll go down to lung cancer, which is now our next device. This one is not a very big market. It's about $6 billion per year, but we feel like the rate at which cancer is increasing, it will soon even pass diabetes, because diabetes is going at, let me check if there are other markets. They call this CAGR, is it compounded annual growth rate? Yeah, for diabetes, it's about 7%. For lung cancer, it's about 18%. So it means cancer is racing. I mean, it's even passing, COVID cannot even reach lung cancer. I mean, I must say, it's very, very fast spreading. Now, you can see from the map here, I don't know where India is. You can see India is so this is the spread of different types of cancers. I think you can see there are only 8 cancers here, but there are many, many cancers. But there's lung, prostate, liver, stomach, colorectal, and all this. But you see how much of lung cancer, how much blue you have here. Many countries are affected. And fortunately, India is not much affected by lung cancer. I can see from this map, and it's taken from a journal published in 2021, just last year. So they did this study on behalf of the WHO. So you can see that lung cancer is becoming a very, very important disease to study. Here, I'm looking at the same paper showing a review of new cases and new deaths from 36 cancers. And if you look at this, you'll see that the female breast cancer seems to have the highest incidence. But when it comes to death, lung cancer, although it's number 2, lung cancer is much worse. Is the first, in fact. You can see 1.7 million people dying just in 2020 from lung cancer. And you'll see that so far, if we look at how many people have died from COVID related complications compared to per annum, you'll see that lung cancer is still above COVID-19. Okay, so this is, then I'm just also giving a review of how many more women or more men, I must say, are affected by cancer of the lung in all regions. You can see from this, for us in Southern Africa is somewhere about 27 compared to 9.3 of women. So almost every country you see that men are mostly affected by lung cancer than women. I think this has something to do with the kind of jobs that men do. They go into the mining business, they go under the ground, they're into so many things. Of course, smoking is one of them, but you can see that men are mostly affected than females. Here in our country, South Africa, we also did some look and see whether we should really go into this. We see that, yes, in South Africa, for men, the biggest problem is prostate, but lung cancer comes to be almost number 4. So I think for prostate, that is something that we still don't know whether it is because of promiscuity or whatever, but lung cancer is, remember, for some of these cancers, it is very easy for you to heal. And if you discover from low stages, but for lung cancer, it's almost like a highway street. You don't come back. If you are stage 2 or stage 3, it's very difficult to come back. Okay, for ladies in South Africa, it's breast cancer, number 1. But of course, lung cancer also is one of the top cancers that even women suffer from. Good, so the problem we have so far is that the traditional methods of diagnosis are many times bulky because they have to be at the hospital. You can see they either CT scan or what you call MRI. All these devices are very big. They cannot be moved around. They are often expensive because you can't just have this in your home and monitor yourself daily. And they're also invasive. Most of them require that you either ingest something like your bronchoscopy, or they have to now pierce through your ribs to get to the lung using the biopsy method. Otherwise, these methods are mostly sensitive when the cancer is already too late. It's very rare that they discover cancer at the early stage with this kind of methods. But I'm happy to show you that with nano materials, now we are able to sniff. I mean, dogs can tell you if they had to speak, but I've seen people using dogs to sniff diseases and telling the master that probably something is wrong with you. See, then when he goes to the hospital, they find out indeed he is diagnosed with some kind of a cancer or whatever, diabetes or whatever. So, but our sensors are like, really, that's why I'm saying sniffer. We call it nano sniffer because it's like a dog that can detect at the very early stage. But at least here, it's better than the dog because we know exactly that this is lung cancer or this is diabetes, because from the biomarkers we can tell. Okay, now it is already known that if you found that you have cancer at a very early stage, you can see survival rates depend on at what stage did we find it. So you will find that at stage 1, A1, you have 95 to 92% survival rate. And that goes down as you go to later and later stages. So it's very, very important that we detect these things at early stage, even when you feel you are healthy. So this is just a report that we got from a business paper. Now, to wrap up on the markets, lung cancer and I would say most of the cancers are in what they call proteomics market. So we got proteomics because it's something to do with proteins and things that they use there. The thing that we are infecting is proteins. Now, in one case, you have our case is in a lab on chip on D, and the other case we only have lung cancer that we already looking at this stage. And then you'll see the monies that you could make just from lung cancer and projected. I told you about 19 compounded annual growth rate of 19.2. If you compare that with diabetes, it's only 7%. So lung cancer is racing, it's really coming very, very fast. And we really need to detect these things at early stages before we can help people. Good. Now, As far as back as 2009, there was a Nature paper. I think you see it there. It's a very outstanding result that gave the impetus to say, let's now, many researchers started now working on this area, because this paper showed that they were able to run through gas chromatography different types of breath of healthy people in green and lung cancer people in red. And then they found that each of those breath biomarkers on your left, you can see hydrazine, carboxamide, blah, blah, all the way down to 610, 42, 610 dimethyl, 5,9 dodecano, blah, 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 all those kind of materials. You will see that this paper put it so nicely. You will see that only number 34 up to 42 are chemicals that are not found in healthy people. So if you find anything that's from 34, that's your 4-methyl octane, 2-ethyl hexanol, blah, 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 up to number 42, you are sure that this guy has cancer of the lung. So it's got a nice paper. I think you can go to it. I think there is a link. You can see from the text, nanotechnology, 2009. So as far back as that. And since then, we were all amazed to see that, oh, there is a possibility that we can even go into this area. So at CSIR, we started a bit late. I was only, at that 2013, I was only joining CSIR. I think I joined in 2012. And I had just become, I'd been a postdoc before, and I joined 2013. Immediately in 2013, we made a device, and that's interesting for you guys in electronics. So there's a chip, and it was patented, and we had, I think, how many countries? Almost now 9 countries after PCT. And this patent has been accepted in almost 6 countries. I think India was included. So India did their assessment, and we submitted our responses 2 or so years ago. We haven't yet got the grant from India. We haven't got the, I think it's India, Germany, but we have had acceptances in major economies like USA, China, Korea, Japan. So when we got the PCT, that's when we realized, oh, we can move ahead. So 2014, the next year, we made a device. You can see in green, the green box. 2014, we have a box that we put this little sensor inside so that we could now do the breath analysis at that level. But so that was version 1. Version 2 came 2 years later. We have nicknamed it MAL4 Nano Sniffer, TM. It was mostly designed for diabetes, but we were fortunate to have also lung cancer patients that we tested at the same time. So you will see that CSR, what they have done so far is they have segmented the device, the market into 2 segments. So there's a hospital market on your left. So here we can make as big as possible because the doctors don't want a very tiny device because they normally, you know, South Africa has this, I don't know in India, but in South Africa, crime is high, so they don't want devices missing from the hospitals. So they want, even if it's a small device, we put in a big box and on a trolley so that they can physically see it. So that if somebody has to take it away from the hospital, you can visibly see that he's taking away something. So, but then the personal market is where we're going to have devices that are small, that can slip into your pocket. And so the two devices, I must say, MAL for glucose is for the diabetes, and lung cancer sniffer is what I'm presenting in this conference. Okay, so, but we haven't gone to making small devices. We are still at using the 2016 model that we have. Good, so when we did this, so these are the results of some of the things that we did. In this research, what we did, we had about 16 lung cancer patients and about 16 normal people who are known to have no cancer. And you'll see that what we were targeting in this study was formaldehyde, acetaldehyde, and propionaldehyde, because these were also mentioned in some papers that it is possible to find these in lung cancer people. And what we found here, you will see that in the healthy and between the healthy and whatever, and the lung cancer. In the first case, figure A, formaldehyde, there's going to be a lot of cross, what you call, lack of distinction. Some cancer people are lower than, having lower levels of formaldehyde than those who are claiming to be healthy. So I don't think formaldehyde is a very good biomarker. Number B, you can see also, there are some cancer people lower for acetaldehyde levels than those who claim to be healthy. So unless they're healthy, the so-called healthy people are not healthy at all. So we probably need to tell them, go and test for lung cancer. But we didn't want to do that because the device is not yet approved. And this was a master's study, a very, very small numbers of people. So we really can't be certain now. Now, in the third case, you'll see, gentlemen and ladies, that propionaldehyde does seem to be a good biomarker because most of the cancer people have it. Whereas those people who are controls, we could not see a trace, except for one patient somewhere there. You see number C, you only have one bar graph there. That's from one patient. But the rest of the patients that were normal did not show propionaldehyde. So shall we call it propanol? It's easier than propionaldehyde. It's an old name. So somehow we have discovered a biomarker here in CSIR for lung cancer, and we are in fact going ahead now to go into stage, what do they call them? The stage 2 of clinical trials. These are now full-fledged, where you have more than 200, 300 patients employed. So we have some money for that to do further clinical trials. Good, and what we also found was that if you get a collective response, this device has 8 sensors. So now we are having collective response on all the 8 sensors. You will see that we could divide this data into, I told you about 16 or so patients. So some patients were of really high stage and the others were of low stage. So you see the blue ones are those who are still very low stage cancer, like maybe 1 or 2, but 3 and 4 were those red ones. You'll see that in both cases, the correlation between our device and the standard GC MS is very high, 87% in the low stages. So which means we can still diagnose at the low stage of cancer, and 95.5%, 47% in the high stage cancers. Okay, and then if you also check when we also looked at, remember our sensors also have a humidity sensor, as I said at the beginning. A humidity sensor was also, we had to kind of see what is happening. Does some patients showed that their breath was very, very dry, like the humidity was very low. So you can see here that when it is still at low stage, the humidity is still good, but cancer tends to remove, the water. They competes for the water that you drink or whatever water you have in your body. Cancer will first of all take that water, and to the expense of the normal cells. So at some level, at some stage, somewhere around 1 and 2, the humidity decreases, meaning that the guy is becoming more and more dehydrated. But I think as stages increase, the cancer now has attacked the whole body, and now cancer starts giving out water. They call this edema condition. I think you can see it from the thing. So you can see the people who have late stages have quite appreciable humidity again, but it's not because they are healthy, but because now they're in edema situation. I think these are the main results of our brief study from this research, but I will also compare we have compared our device with the other devices that we see on the market. You will see that in the first column of the table, we have the samples. So each method, whichever method that you use, will in fact expect you to bring a certain kind of a sample. So in the first case, they have DNA. I think they call it circulating tumors DNA, and CT for circulating tumor. And the analysis method there is multiplex PCR. And I think most of you guys have, if you test for COVID-19, they use PCR to do that. I was expecting this to be very, very sensitive, but from this review, which I see, it's a review by Zen, Lee, Jinan, blah, blah, and it's, if you check in the table for description or legend, they published this in Oncology Letters just 2 years ago. So they gave us this table. You see that PCT is not as good, it's not as sensitive, but I don't know why governments are forcing us to test only by CT, I mean by PCR. You see 40.0 to about 59.0 is a percentage sensitivity. Okay, and then we have all the papers, 14 to 16 reference, I think, in the actual document that I wrote, I have these references. Maybe I cannot show them in the PowerPoint. In the second method, they use bisulfite conversion plus PCR. You will see that there's improvement 70 to 87. Then you got your microRNAs as a sample, but you use NGS, and NGS, there's an acronym in the legend. NGS is new generation sequencing. So, and there's all these methods, FISH and IF. FISH is standing for, come on, it's already on the immunofluorescence, it's IF, and FISH is fluorescence in situ hybridization. So you will see that all these methods, I was amazed to see none of them goes into really 90s and whatever, very close to 97, 90, 98% sensitivity, which is what probably FDA and CE would really require. But exhaled breath goes straight to there. You can see exhaled breath, exhaled VOCs, which is volatile organic compounds, by GC is 81, by PTRMS 82, by IMS 81, LPPI MS is 81, but a sensor that is like the type of our sensors, but these are electronic noses, they have 92.5. And in our case, the very first study, we haven't even done 200 patients, but in our very first study, we can see that amongst those that are early stage, we can go to 78, but those of late stages, we can go to 95 of 96%. So this is quite encouraging, and we have asked for the full clinical trials now, and they have given us the fund. So we are entering into clinical trials next month. Otherwise, I think this should be the end. I didn't have that many slides. Thank you very much for your attention, and I'm inviting discussion or questions. Thank you.
Thank you for an excellent talk. Now this is open for discussion.
Professor, it was a wonderful talk. How long it took from the basic idea to all the way going up to the prototype product, and how long you think from here it will take for you to take it to the market?
Oh, very good question. Thank you very much, Professor. As I said, I joined CSR like 2007. I was still a PhD student, and at that time, I don't know if Srija is in the conference. Srija Pillai, she was our postdoc that time, but so we used to interact very well with especially developing nanostructures and all that. That time we were more interested in producing, you see, nanomaterials, because the excitement 2007, 2008, and all this was to bring out, did I get nanowires? Did I get nanotubes? Did I get, you see, it was exciting that time. But as it came to around 2013 and all that, people were concerned more that when can nano bring any product? So I would say it took me from basic research to having products 2007 up to 2013. That's almost 6 years, I must say. But I must warn you, if you were fully doing research, you should take less than that. But because remember, we also have to supervise students, we have projects with students, and sometimes we are taught to publish our work and be able to declare publications every year. It kind of delays all this product development. But I know publications and other students must happen. But for us to make a product, you need time for this. So yeah, 6 years or so to move from the lab to at least products, and then not product, let's say prototype. And from prototype to product, no, prototype means you have to test it in actual environment, and people must, the customer must be able to accept that, yes, I like your idea and I'm putting so much money on this. That takes also maybe another 5 years or so. So it's really like not going to sell what you call samosa, make samosa and sell and you get money today. No, this is long-term investment. You put in a lot of money at the beginning and a lot of time, a lot of thinking, and then you reap the benefits. Now it will be billions, because this product of breath analyzer has been valued at 1.3 billion rand. I'm not sure how to convert to rupees. I think rupee and rand is it two rand to 1 rupee? I can't remember. So just divide by 2 if you want to see how many rupees. It's still billions of rupees anyway for the product. And yeah. So
Thank you so much. I just want to know, are you also working on other type of cancer detection?
Yes or no, because with CSIR, when they tell you we have this problem, you tackle that problem. But as a professor at the university, I also do other things. We also have medication. In fact, there's a student working on medication for breast cancer. We did find a certain herb that would be probably is not in electronics. This is now in bio. So this is a biochemist student that I'm having at the TUT. She does extract materials from. So we do not detection per se, but we have medication for different types of cancers. We have tested them, and we need now to do they call it what? Sensitivity tests, which means we must have the cancer cells there, and then we see how we can kill them. But we did kill breast cancer cells. Now we need to move to other kind of cells. Even if we can see prostate cancer cells, we'll see how. Then next time we'll be just giving you some tablet. If you have prostate cancer, we just give a tablet that you can take, which is much better than chemotherapy, much better than your what people are doing today, even the radiotherapy, because all these things are very, very invasive. So yeah, testing. Yes, we also do malaria. I have a breath analyzer for malaria. We have biomarkers for malaria, which CSR is also trying to put in the pipeline. We also have a breath analyzer for TB. But all these things are in the pipeline. We still have to test them in the actual environment.
Thank you, Bruce.
Thank you. Can I ask one question to the audience, maybe discussion? Why is India, right? Why is India in this case is showing a lot of lip and oral cavity cancer? This is
see that India is having more on oral cavity cancers and all because of tobacco chewing is one of habit is there in India. More of.
Oh. Yeah, thank you. Now I was really, this map was disturbing myself, but why is India? Okay, it looks like it's safe from lung cancer, but it does have a problem with lip and oral cavity. So, okay, thank you very much for this. Thank you very much.
Yes, so what is the sensitivity and specificity of this product, sir?
Okay, the sensitivity, I showed in the tables there, ranges from 78 all the way up to 95.7.
So how many clinical trials you have conducted on how many people, sir?
One so far, and again, as I said, it was a master's project. So we are now going to full-fledged clinical trials. So this was very few patients, about 13, if not 15 lung cancer, and 15 normal patients.
Okay, okay, sir. Thank you very much for this very good talk. Thank you, sir.
Bye-bye. Sorry for coming late. I was in a crucial meeting. I think these bosses just tell you, come. Said, okay, I'm trying to go to a conference and say, no, but let's discuss this fast. Okay, so I took long, sorry.
No problem at all. In fact, we know that you are under very busy schedule. Sorry to disturb you also, because because it was this conference was going in time. That's why. Sorry, sir. But thank you very much.
Thank you.
Time for us. Thank you very much.
Good. Can I stop sharing now?
Yeah, you can stop sharing, sir.
Okay. Okay. Thank you, Dr. Sima. Is this Sima or Sema?
Yes, Sima. Sima.
Sima. Ah, okay.
Yes.
Okay.
Okay. Thank you, sir.
Thank you.
So our next speaker is Dr. Milan Kulkarni. Dr. Milan Kulkarni is working as senior scientist and group head in Nano Composite Laboratory, CMET Pune. Dr. Kulkarni has published more than 100 research papers in international journals of high repute. He has filed more than 20 patents, including US patents. And his field of interest includes nanomaterials and polymer nanocomposites for multifunctional applications, development of conducting electroactive polymers and their nanocomposites, flexible and wearable electronics devices, and nanomaterials for inkjet printed and flexible electronics devices. And he is the recipient of the prestigious Young Associate Award in 2009 and Fellow of Maharashtra Academy of Sciences. He is the life member of Materials Society of India, MRSI, and the Society for Polymer Science. He is also an expert for Techno-Novus at Automatic Research Association of India, ARAI, Pune. Dr. Kulkarni has designed and developed first indigenous and low-cost polymer swab for the sample collections and testing of COVID-19 and other viral disease. So he has done a great job during the COVID period, pandemic period, and he has developed a totally indigenous and low-cost polymer swab. And our hearty congratulations to you, sir. Over to you, sir.
Good evening, all. Hello.
Milan, you are audible. You are audible.
Yeah, I'm audible. Okay, fine. My screen is visible to all of you.
No, you have not yet shared.
Okay. Just give me 2 minutes. I will share my screen. Now it's okay, madam?
Yes.
Hello.
Yes.
Yeah.
You can start your presentation. It's in screen.
Well.
Yeah. Your screen is shared. Okay.
Yes. First of all, I would like to express my sincere thanks to organizing committee World Sensor Congress for giving me an opportunity to present my research work or activity, I can say. Yeah. So thank you, Sima, Dr. Sima, for such a nice introduction about me. Yes. Okay. Hello.
Milan, you are audible. You can start your presentation.
Madam, can you just change the slide from there or from here? I have to change my slides.
You have to change from there.
Okay.
Dr. Milan, still it is in the first title slide only. Dr. Kulkarni, can you hear us?
Hello.
Yeah, still it is the first slide only. Kindly change it.
Yeah, I'm not able to change the slides from here.
No, you change the slides from there. Can you share your entire screen first? Have you done like that? Entire screen you take?
Slide is not. Yeah, just a minute, madam. Okay.
Now it is changed. Now it is changed.
Yeah, very good. And sorry for the interruption. Yes. So, good evening, one and all. So, I'm going to present my research work on nanostructured polyaniline and its nano composite, a material for multifunctional sensor applications. So, we all know that polymers are typically utilized in electrical and electronics application as an insulating material, because we are taking the advantage of their high resistivity into our day-to-day application. The typical properties of polymeric materials that they have high strength, good flexibility, elasticity, stability, and moldability, so that we can convert into a desired shape what we are looking for a different application. And the most important thing is that about this polymer is ease of handling, which is very much important. Yeah, I could not control myself to show this slide because in the year 2000, the Nobel Prize was awarded to three scientists, Professor Alan Jaeger, Professor Hideki Shirakawa, and Professor Alan McDiarmid for the discovery and development of the conducting polymers. Yeah. On the screen here, you can see the different conducting polymers like polyacetylene, polythiophene, polypyrrole, polyparaphenylene, and polyparaphenylene. But in my talk, I'm mostly going to talk about the conducting polyaniline and its nanocomposites. Here you can see the typical range of conductivities of insulating material, semiconducting material, and that of the conductor material. So nylon and glass, which is well insulated, have conductivity in the range of 10 to the power -16 to -14 Siemens per centimeter, while the metals like copper, silver, they have the conductivity in the range of 10 to the power 3 Siemens per centimeter. However, the conducting polymer lies their conductivity in between the semiconductor region. However, additionally, we can tune their conductivity from insulator to semiconductor and semiconductor to conductor regime by changing different dopants as well as by changing different synthetic processes. Okay, so interestingly, conducting polymer is the best combination of metal properties, that is electrical properties of the metal, and the polymeric properties such as lightweight, greater workability, and resistance to the corrosion. So thereby, these materials has become an attractive or applicable in materials for the 21st century. Yeah. So there are certain advantages with the polyaniline among the other conducting polymers, and I have listed them as the monomer aniline, which is very cheap and available abundantly. It has a very good environmental stability. The synthesis of polyaniline via oxidative polymerization process is a very easy process, thereby ease of preparation is there. And it has the low temperature processability so that we can convert or mold this polymer into a desired application. And the most important thing is that the yield obtained is very, very good, and we can get a high yield after chemical oxidative polymerization. And the most important specialty is that during synthesis, no any special precaution or expensive catalyst is required for the polymerization process. Okay. Yeah. So then why we have to move towards the nanostructured polyaniline? Because whenever you will synthesize polyaniline from the aniline monomer via oxidative polymerization process, you will land into the free-flowing green color bulk size polyaniline powder, which is non-processable and non-soluble in common organic solvent. There are certain organic solvents are available like metacrosol and N-methylpyrrolidone. However, these solvents are not recommendable for multifunctional, processability applications. Thereby, there are restrictions, and hence the properties of polyaniline can be modified by converting them into the nanostructured material. So the nanostructured polymer has an advantage of combining the organic conductor with the low-dimensional system. The most important thing is that it has a very high surface to volume ratio, which is very, very important as far as sensor application is concerned. It can also have a surface free energy and high electrical conductivity. So these are the advantages of the nanostructured polyaniline, and therefore worldwide the research is going on for the development of nanostructured material or nanostructured polyaniline compared to that of the bulk counterpart. So here we have synthesized this conducting polymer polyaniline via novel interfacial polymerization techniques. Friends, here we have taken the advantage of the solution chemistry. That means when the organic and aqueous phase you have mixed together, there is a formation of boundary between the two phases, because the organic phase and aqueous phase are immiscible with each other, and the boundary between the organic phase and aqueous phase in nanometer regime. So here what we have done, we have taken the carbon tetrachloride as a solvent to dissolve aniline monomer, and acid, which we are using for the doping purpose, we have dissolved in water along with ammonium persulfate as an oxidizing agent. So instantly we have mixed these two phases into a sample bottles, and immediately there is a formation of boundary between these two phases. And when the monomer molecule present in the organic phase come in contact with the oxidizing agent present in the aqueous media, the polymerization started, okay, at the boundary or at the interface. The monomer molecule get reacted with the oxidizing agent and get polymerized, and immediately they can diffuse into the water phase, okay. So thereby what happens, the second front or next monomer molecule will come into the contact with the oxidizing agent, and the polymer chain reaction will proceed. So to our surprise, when we have characterized this nanostructure, the material collected at the interface, we observed there is a formation of nanofibers or nanorods of polyaniline having the diameter of around 200 nanometer and length up to few microns. Okay. So one of my PhD student who is organic background and organic chemist, she has taken or she has carried out this reaction by using separating funnel. Thereby, the isolation and separation of the polymer form at the interface was very much easy, and we can give the sufficient washing to the desired product. And then we have characterized it by PCM analysis, and we have observed that we got a very uniform size nanofibers of polyaniline. Yeah. So why there is a need for innovation? Because whenever we have carried out the application of this conducting polymer for humidity sensing application, yeah, we observed that the free flowing powder that we have received or we have synthesized by bulk polymerization is a free flowing powder. Then we have converted them into the pressed pellet form by applying the suitable pressure, and then we have connected we have made contacts with the silver room temperature curable silver paste with the copper wires to connect it to the multimeter, and we have used standard 2 temperature method for the humidity change, which is very standard process for the calibration of the commercially available sensor instrument. Then after few cycles, we have observed that the contacts will get loosened from the surface of this pellet, and therefore we have tried with further attempts that we have dissolved this polymer into a suitable solvent and casted a freestanding or surface adhered film and maintained the contacts as I have mentioned in earlier. And we have carried out the sensing performance or measurements by using this coated electrodes on a glass substrate. But we observed that because of the one substrate of the film is adhered to the glass, only one side or one portion will get exposed to the humidity, and we are not getting the realistic or reliable data. So later on, we made freestanding films of polyaniline by dissolving onto some organic solvent and casted it on a variety of substrates. Okay, so we made a prototype device by connecting this IDT pattern. In a very first day, Professor Gangal Madam has given the invited talk on polymer-based sensor, and during her presentation, she has mentioned there are two types of sensor devices. One is resistive type and other one is capacitive type. So we have here prepared the IDT pattern on a FRP substrate coated with the copper electrodes to get a better understanding and reliable data for individual fingers from this sensor device. And we have casted a film of polyaniline and performed the sensing measurements. With the help of some electronics engineer and my project staff and research students, I made a prototype table-mounted device where you can see the change in humidity in %RH, as well as it will show in the display form. With the further attempts, we have used some sulfonic acid dopant to make this polyaniline into an ink formulation. Here we have used dodecyl benzene sulfonic acid as an organic acid to dope this polyaniline, and when we have synthesized this polyaniline by using ammonium persulfate as an oxidizing agent and dodecyl benzene sulfonic acid as a sulfonic acid, we observed we got a formulation which is soluble in water, ink formulation. So to my surprise, what I have did, I have taken out the cartridge, okay, from this inkjet printer, which is originally filled with the carbon ink. I have taken it out by a syringe and I have cleaned thoroughly with the organic solvent. Then I have once I have ensured that the original carbon ink has been totally removed and now the cartridge is totally free and clean. I have filled this ink formulation, polyaniline-based ink formulation, by using another fresh syringe. And to my surprise, I have prepared this IDT pattern in a PowerPoint presentation. And instead of filling or feeding, this our normal cellulose paper, I have fed it with the OHP transparency sheet, that is polyester sheet. And by just clicking a OK command or print command, I could able to successfully transfer this pattern of IDT pattern. Yes, on the flexible polyester sheet. Yes, this is nothing but the first step towards the flexible one. Yeah, madam, I am audible or echo is there?
Dr. Milan.
Yeah.
Dr. Milan, lot of echo is there. I think you are using two devices. Are you using two devices? If so, please mute one of that.
No, sir. I am using only one device only.
But still a lot of, I don't know, somebody else has kept their mic on or something is happening. Yeah. Okay, all others kindly mute, please. All others kindly mute. Yeah, you kindly go ahead.
Yeah, now it's okay, sir.
Yes, definitely better.
Very good, thank you. So we have filed immediately Indian patent for this, and we have published this work in Smart Material and Structure in the year 2012. Okay, so here you can see a very fast and very interesting humidity sensing response for a broad range of humidity ranging between 10% RH to 100% RH, and there is a linear drop down in the resistance up to say about 20% RH to 80% RH. However, at a higher humidity there is a slight saturation, but definitely we have measured the on-off cycle, and here you can see there is a very fast switching on and switching off response, which is just few seconds, and this is a very fast response for a broad range of humidity for the polyaniline based flexible and printed humidity sensor. These results we have published in Sensor and Actuator Journal in the year 2013. Okay, so the similar ink formulation we have used for the development of electronic nodes based on the polyaniline, and we have observed very good on and off response, which is very fast and detectable, and which is very selective for the methanol and ethanol sensors. So we can use this device as an electronic node for a breath analysis purpose or as a breath analyzer for drunken driver. We have filed immediately patent for this invention as well. Okay. Yeah. Then we have tested this polyaniline for different volatile organic compounds like benzene, carbon tetrachloride, chloroform, and so many things as well as toluene. And we got a very on and off, very fast switching on and switching off response for these organic vapors as well. Okay, so now I will slightly move to the nano composite, because only conducting polyaniline or polymer matrix is not suitable or is not giving the reliable and good quality result to achieve the sensitivity and selectivity, which are the important parameter as far as sensor is concerned. So we can dope them by using some one-dimensional or two-dimensional material. So nanocomposite basically incorporation of nanoparticle into an amorphous material or porous material. So polymer nanocomposite is nothing but the combination of polymer matrix and inclusion that have at least one dimension, that is either length, width or thickness in nanometer range. Okay, so we can use three-dimensional nanoparticle like silver metal nanoparticle, copper nanoparticle, gold nanoparticle, so on and so forth. Or we can use one-dimensional carbon nanotubes, multi-watt or single-watt nanotubes. And if you cut this one-dimensional, carbon nanotube by using a cutter and just flatten it, it will become a two-dimensional nanosheet. That graphene also we can use to prepare the nanocomposite. We can use different polymeric matrices like thermoplastic resin like polyester, PVC, PMMA, and so on and so forth. Thermoset resins like phenolic, epoxy, and amino, and elastomers like natural and synthetic rubber for making this polymer nanocomposite, depending if the final use or the application part of this nanocomposite, where we need a flexible and bendable device. Then in that case we have option or choice to use the elastomer to prepare the nanocomposite, and we can use different nanofillers like CNF, CNTs, metallic nanoparticles, MMT, and other material to make this polymer nanocomposites. Okay, there are three different methods to prepare. One is solution processing, melt processing, and in situ polymerization. I'm going to focus mainly on the in situ polymerization technique, because here there is uniform distribution or dispersion of the nanomaterial or nanostructure material into the polymer matrix. These are the certain applications of this polymer nanocomposite in a broad area like optical computer, chemical and biochemical sensors, polymer LEDs, conductive additives, so on and so forth. Okay, yeah. So now I will give a case study of conducting polymer carbon nanotube nanocomposite. We have taken the advantage of exceptional electronic, mechanical and thermal properties of carbon nanotube and the advantage of conducting polymer like low cost, light in weight, flexibility, photonic properties and simple processing method into this carbon nanotube polyaniline or carbon nanotube polymer nanocomposite. So here what we have done is, we have the pristine carbon nanotube. If you dissolve in either water or organic media, they have tendency to settle down because of the gravitational force. So we have to modify or functionalize this carbon nanotube by acid treatment. So for that matter, we have treated this pristine carbon nanotube, multi-wall carbon nanotube with sulfuric and nitric acids, and usually or generally this functional group carboxylic acid will get attached to the top and bottom end of this carbon nanotube, or either fractured side on the carbon nanotube. And because of this repulsive force between the similar charges, this functionalized carbon nanotube tends to repel or keep repelling each other and get suspended into that organic solvent or aqueous solution. Then we have added aniline monomer into it, and by adding oxidizing agent, we have initiated the polymerization reaction, and we observed and we have got a green color CNT polyaniline nanocomposite. But when we have subjected this for the Giessen analysis, we observed that there is a very beautiful core shell-like structure. Here you can see the core part is nothing but your gray color carbon nanotube, which is very uniformly wrapped with the polyaniline or a green color conducting polymer to form a core shell structure. And that we have confirmed by TM analysis. Here you can see the dark black color is nothing but your carbon nanotubes, and the grayish color is a thin layer of conducting polymer. Also, we have characterized it by using UV visual spectroscopy, FTIR spectrum, XRD, and thermal technique like TGDT. So, what will be the use of this, overshell carbon nanotube polyaniline composite that we have dissolved or dispersed very well into the aqueous media? And here you can see, as we change the pH of this, dispersed solution from highly acidic pH to highly basic pH, that is from pH 1 to pH 12, there is a beautiful change in the the color of this polyaniline, because at different pH the oxidation state of the polyaniline changes from conducting emeraldine salt phase, which is green in nature, to the insulating quernigranulin phase, which is blue in color. So we can use this material for optical pH or optical sensing at different pH, ranging from a broad range of pH 1 to pH 12. Later on, we have coated this on an optical fiber and developed a flexible, one-time use, a very low-cost optical pH sensor device. We have filed a patent for this, and we have published this research in Sensor and Actuator journals. With continuous efforts of that, we have used some cotton cloth to coat this formulation on a cotton cloth material for a wearable sensor application, and we have followed a simple dipping and drying process to develop this e-fabric for wearable electronic devices and applications. So here you can see we have demonstrated the illumination of LED via molecular wire made up by using carbon nanotube polyaniline nanocomposite and your cellulose-based threads. So 1 meter long thread, you can see we have connected it to the 9-volt battery and LED, and it has shown a very good conductivity unless and until we disturb or disconnect it from the cell or to LED. The illumination of light we observed very bright in nature. This is a proof of concept to show that the insulating cotton fabric will become highly conducting when we coat with carbon nanotube as well as polyaniline nanocomposite. So we have observed a very good effect of loading of carbon nanotube percentage into this composition, and it is very trivial that as you increase the concentration of carbon nanotube into this nanocomposite, the conductivity is found to be increased linearly, because the carbon nanotube has a very good conductivity and will get enhanced along with the polyaniline, and it has shown a very good conducting nature. So we can use this lightweight conducting wearable fabrics for micro-absorption, static charge dissipation, EMI shielding application, and selective detection of gases and biomolecules. That means we can incorporate this as a wearable sensor. Okay. Definitely, these are images I have taken from the Google, so we can use this conducting fabric as a textile-based electrode or textodes, because at presently to collect the signals from ECG and EMG, a silver-based gel is used, which has certain people and neonatal babies, they have allergy with this silver gel. So for that matter, we can use this conducting based fabric to develop a smart textile-based electrodes. And in epileptic person, we have to continuously collect the signal from the brain. So we can make a smart cap by using this conducting or smart fabric. Okay? Yeah. So in a similar fashion, we have synthesized silver polyaniline nanocomposite. Friends, I would like to show a very one interesting thing here. Just by changing a dopant acid from PTSA, that is paratoluene sulfonic acid, to dodecyl benzene sulfonic acid, we can control the diameter of the this nanocomposite material. Here we have used paratoluene sulfonic acid as a dopant along with oxidizing agent, and by subjecting the nanocomposite to FECM analysis, we have observed the diameter of this rod, nanofibers is around 100 nanometer, having a length up to few micron. In another experiment, we have just changed the dopant acid that is from PTSA to DBSA, and we have observed that there is a reduction in the diameter of this nanofiber from 100 nanometer to exactly half that is 50 nanometer. So friends, to do the nanoscience and nanotechnology, we don't have to need a very sophisticated and costly equipment and chemical. By taking the advantage of this, dopant acid as well as organic chemistry, we can tune the properties and structure of this nano-structured polyaniline. Here you can see this polyaniline nanofiber is observed to be beautifully decorated with this black triangular shaped silver nanoparticle, and we have successfully used this for antibacterial activity with our collaborator at University of Pune, and we have published this paper in Poroidine Interface Journal Biointerfaces in the year 2012. And this silver polyaniline nanocomposite has shown a very good antibacterial activity as compared to your pure or pristine silver nanoparticle, because at bulk silver nanoparticle, the growth of the colonies of this microorganism is observed at the end or peripheral region, while in polyaniline and silver nanocomposite there is a continuous time-based release of the silver nanoparticle, and thereby we observe a very good antibacterial activities. Later on, we also have prepared only pristine silver nanorods, and we have utilized or used it for antiquorum sensing application, and we have published this research in applied microbiology and biotechnology. Okay, then we have prepared this polyaniline silver nanocomposite coated fabric for a smart bandage application, okay, for wound healing application. Here you can see these are the nanofibers or fibrils of this cotton cloth, which are uniformly coated with this silver polyaniline nanocomposite. In a similar fashion, we have prepared cobalt polyaniline nanocomposite, and this research we have published in Talenta Journal, and we have used it as a big semiconductor, room temperature magnetic semiconductor, and we have published this research in the Journal of Magnetism and Magnetic Material. Here you can see these cobalt nanoparticles are attached with weak van der Waals forces of attraction with this nitrogen atom, and they have remained there itself in a dispersed state. Okay. Then later on, we have worked on a polyaniline manganese oxide nanocomposite via interfacial polymerization technique. And here, I am very happy to show a very beautiful morphology of this nanocomposite, just like a kadamba flower or marigold flower, having a more open morphology, which is very much important for photocatalyst application as well as energy storage devices. And we are testing this material for lithium-ion battery applications. So now we have diverted our research, and we have initiated some research activity for the development of sensors by using conducting polymer as well as some nanostructure material like gold nanoparticle, carbon nanotube, and graphene, reduced graphene oxide, coated on this screen printed electrodes for the dentistry application. And by taking the advantage of optical properties, we can convert them into a different pH levels, and we can use them for biosensing application, because in dentistry itself is a ocean, and there are a lot of applications because of different foods and beverages. There is a change of the pH level, and which will very easily get detected by this polyaniline, and we will get a very detectable signal into optical signal for monitoring these devices. Okay, we have also prepared silver vanadium oxide polyaniline nanocomposite for energy storage devices as a supercapacitor and battery as well. Madam, how much time I have? Dr. Seema, madam?
Hello.
Yeah.
Including discussion, you may have 10 minutes more. Okay.
Okay. Just briefly, I will explain other things that we are doing. Okay. So we are developing nanostructure material for radiation screening, particularly X-ray absorption purpose. At presently, we are using lead or lead-containing compounds for the development of lead or X-ray absorbing material, but lead is very toxic, costly, and is heavy. So we have decided to eliminate the lead. That will reflect in the reduction of the cost as well as reduction in the weight. Because presently the doctors are using this lead-containing apron and having the weight of around 5 to 7 kg, and it is very difficult for the doctors and X-ray operator to use this apron continuously because it will develop the back pain problem. So CIMET has taken the initiative and we have totally removed and replaced the lead, and we have developed some nanostructured material and we have compounded it with the polymer formulation to coat it on a cotton cloth, and we have fabricated this prototype apron, and the weight of this apron is just 2.2 kg, and it has shown a very good X-ray attenuation properties which has been certified by Atomic Energy Regulatory Board in BARC, Bowel Atomic Research Center, and there it has shown that this lead-free or nanostructured material containing apron developed by CIMET has shown a very good X-ray attenuation property. We can use this for X-ray scanning at the baggage on the airport, and we can develop the biomedical devices like apron and gloves for X-ray rooms. In a similar fashion, we have developed the glass nanocomposite as well. I'm not expert in a glass, but definitely we can use this glass nanocomposite for viewing purpose to fabricate the X-ray rooms. Okay, this is the mechanism. Actually, I will not go much detail into this. The media has given a very good coverage for this invention. We have filed 2 patents, one US, one PCT, as well as one Indian patent, and this technology is ready for its commercialization. Then now we are also focused on the materials for energy storage devices. As we all know, we are using batteries and supercapacitor for different applications, and I will be happy to show this slide because in the year 2019, the Nobel Prize was awarded for the discovery and development of lithium-ion batteries for Professor Goodenough, Stanley Pittigam, and Akiro Yoshino for the discovery and development of lithium-ion batteries. So at CIMET Pune, we are working on the active material, that is cathode active material and anode active material for lithium-ion batteries. I will skip some of these slides because of time constraint. Okay, yeah. So we have created, entire battery fabrication facility. Okay, the process equipment, some characterization equipment, and the entire battery fabrication and testing facility, which comprises of 19 altogether equipment, and we have accommodated them very nicely into a battery fabrication and testing facility. Okay, this is the glow box, which is nothing but the heart of this battery fabrication facility, because we are using a liquid electrolyte, that is LiPF6, which is moisture and oxygen sensitive. Okay, so as on date, we have developed 4 different materials, that is traditional lithium cobalt oxide by sol gel method, as well as by hydrothermal techniques, and we have characterized it by using different characterization technique. We also have developed LTO as an anode material, which is a free-flowing, white color powder. And here you can see there is a lot of pores, highly porous or interface in between, and which is very important for the lithium intercalation during charging and discharging. And we have fabricated button and pouch type of cell, and we have observed very good capacity milliampere hour per gram as compared with the commercially available material. With our further attempts, we have synthesized spherical hard carbon as a replacement for the graphite, which is an anode material presently being used. And the beauty or important thing of this material is that we have used potato and banana as a starting material to synthesize this spherical hard carbon. We have characterized it and fabricated more than 300 of button type of cell by using the in-house developed material. We have tested them, and we also have prepared this pouch or rectangular type batteries by using this material. With further attempts, we have developed a large size, that is A4 size pouch type of cell for EV applications. Then we are also working on the development of flexible electronics, because the trend of flexible electronics is coming into the market. And to power these flexible electronic devices, we need batteries or energy storage devices also to be flexible and bendable in nature. So we have developed this flexible electronic batteries for flexible electronic devices, and we are using electrospinning techniques to prepare the freestanding three-dimensional active materials. Here you can see we have prepared the polymer based separator having high porosity as well as electrode material. We have also developed a solid state separator membrane or a solid electrolyte for a complete solid state batteries. Okay, this is a prototype that we have developed into our laboratory, which we can bend it, twist it, and there is no fidelity. We can observe even if you twist or roll the battery, flexible battery, there is no fidelity in the intensity of the glowing LED. Okay. So this is the prototype that we have developed of the flexible or bendable battery in our laboratory. We have tested it by changing the different bending angle as well as at different temperature, because we want to utilize this battery at different geographical location from Siachen to Rajasthan, where there is a variation into the temperature. With this further attempt, we have made one wearable, this biomedical device, or you can say a watch, which is powered by this flexible and bendable lithium-ion battery. We also have prepared this transparent lithium-ion cell, a prototype or battery, by using polydimethyl siloxane as a material. Okay. Yeah. Then we also are working on a sodium-ion batteries, and we have developed various nanostructured cathode and anode active material, and we have fabricated a coin type of cell for sodium-ion battery. So, as Madam has mentioned, we have contributed, by developing a polymer swab during this COVID-19 pandemic, and by using polypropylene rod and polyester fiber, within an 8 days period, we have indigenously developed a very low cost a polymer swab for COVID testing, and this has been approved by the ICMR and NIV, that is National Institute of Virology. Media has given a very good coverage for this research activity. This is the research activity for a social, activity, under a social activity. Okay, so I will come to conclusion. So we have developed this conducting polyaniline via interfacial polymerization, and we have converted from bulk to nanostructured material. We have also prepared the nano composite with silver, cobalt, and gold nanoparticle as well as carbon nanotube, and we have used successfully for biological applications such as antibacterial and antimicrobial activity. We have tested them for humidity sensing application, and the polyaniline based ink which we have prepared and synthesized by using sulfonic acid dopant. We have used them as a flexible or flexible humidity or moisture sensor, as well as an electronic nose for volatile organic compounds, and we can detect various diseases as well. We have prepared polyaniline MWC nanocomposite for optical PS sensor, and we have also used for development of smart fabric for biomedical application. And by development of nanostructured material and polymer nanocomposite, based on low cost, we can develop the indigenous sensor for dentistry. The work activity has already initiated in our laboratory. I would like to sincerely acknowledge the help from Ministry of Electronics and Information Technology, our parent ministry, our Director General Dr. B.B. Kale sir for his encouragement. And I would like to acknowledge my all colleagues, students, project staff from the Nano Composite laboratory. Because of them, I could able to present this result. Thank you very much. Please visit our CMET website, and any question or queries, you can write to me on this email address, milin@cmet.gov.in. Thank you very much.
Thank you, Milan, for this wonderful talk. I know I have given you a very short notice.
Yes, thank you.
Thank you very much, because you have helped in contingent situation. Thank you very much for that also. The forum is now open for the discussion. I have seen one question in the question answer section, and that is from Ajay Pradap Singh. The question is on for which gas, ammonia or NOx, Pani nanocomposites are most sensitive, and why?
Yeah. It is mostly sensitive to chlorine vapor as well as for ammonia also, because there is change in the oxidation state of the polyaniline. Okay. when we expose to ammonia, I mean, it will get changed from conducting emeraldine salt phase, which is green in color, to insulating pernigranulin phase, which is blue in color. So, I mean, effectively, these polyaniline nanofibers are highly sensitive, equally for ammonia vapor as well as for chlorine or HCl vapors. Hello.
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 Yeah, anyone else have any questions to be asked, please?
Any more questions?
So I think that due to want of time, we can stop the QA here. We will request all the participants who are having any queries, please write to Dr. Milan. And Dr. Milan, thank you very much for your wonderful talk, as well as helping us in a contingency also. Thank you.
Thank you very much, madam. Thank you. Can I leave the screen, ma'am?
Yeah, you can now sign off from this.
Yeah, I will stop sharing. Yes.
Yes, thank you.
Thank you. Thank you very much.
Hello. Yeah,
Hello.
now we will move on to the next speaker, Dr. Animesh Jha. Dr. Animesh Jha is a professor at University of Leeds, UK. He has published more than 430 research papers in peer-reviewed journals and conference proceedings, and he has more than 30 years of experience of managing large, medium, and small-size grants supported by various bodies such as European Union, US Military, UK Defence, British Council. And he is the author of the book on inorganic glasses on photonics. His research interest includes processing of rare earth doped glass ceramics, thin films via pulsed laser deposition, optical fiber engineering for lasers, sensors, and amplifiers, and materials engineering for optical integration, interaction of lasers with biological matter, which includes dental minerals, bonds, and soft hard tissues interface engineering, and 2D MOS2 and graphene materials processing using laser. So he's a very eminent personality, and I request Professor Animesh Jha to deliver his talk. Over to you, sir.
Can I share my screen, please? I don't have rights.
Dr. Karthik, please give the...
Yes, sir, you can share the screen now. You are permitted now.
Okay. Just a moment. You see my screen now?
Yes, Professor.
Okay. Good morning from United Kingdom and good afternoon in India. As I have been introduced, my name is Animesh Jha. I work here in the University of Leeds in the School of Chemical and Process Engineering. My field of specialization is optical fibers, glass materials, and also looking at spectroscopic properties of materials, including biological materials. I'm quite involved at present in medicine-related projects. This is a piece of work which I'm going to present was completed between 2009 and 2017, I would say. It included looking at materials, characterization of food products, as well as human tissues, other kinds of biological tissues, using infrared spectroscopic techniques. So this presentation is divided into few parts. And primary focus is to look at now the opportunities in the diagnosis of chronic diseases. And I'll take just one example, but before I do that, I want to go through the process of how optical fibers work. So I'll take some time because I'm not sure the spread of knowledge in this area. So it's fair to introduce that and why biophotonics is important. What can we achieve? And if we want to combine optical fibers with biophotonics, what are the things can we do? So that's basically the talk. So you will see some examples. So let's think about optical fiber waveguide as biophotonics tool. What can we do? So first of all, we need to design a proper waveguide or an optical fiber. You have to have a source of light to guide through the optical fiber. You have to have a detector at the other end of the fiber to see the signal. And then you can think of producing an image or get a data, and you can process the data for taking any decision. The latter 2 points are extremely, extremely important. I cannot overemphasize this point. And this all comes in the part of data science, artificial intelligence, all those things you think of, deep learning, computer science related techniques, and engineering, data engineering, producing images from the data. So they are there are big opportunities in there, which I'm not going to talk because I'm not an expert in that area. So although, just to give you a very brief introduction, people knew that light can be guided through medium, particularly long time ago in 18th century, people used to guide light through flow of water. And you can see this kind of information is available on YouTube's. Then first time serious studies began in 1940s, and momentum gathered during World War II. High quality quartz became available, and back in post World War period, late Professor Narendra Kapani, who was honored last year, or by maybe in 2020, by the Prime Minister Modi. He was at Imperial College London doing his PhD, and he published an article on guiding light to obtain image. And he showed this in beautiful article in Nature journal. And he showed how the glass air light wave guide can bend light and produce an image. So he showed that. But further development on really ultra high purity optical fibers were carried out in 1966 by Professor Charles Cow and George Hockham at the
Nortel Research Laboratory in Harlow in England. And they showed how the total internal reflection is taking place. And they also use Maxwell's equations model for demonstrating the propagation. So theory and practical both came together. Whereas the Nature paper by Capani showed experimental evidence for propagation of light. There is no description of the theory of light. So this was these two pieces of work were wonderful pieces of discovery, which revolutionized light propagation in a guided media. Let me walk you through what, just like if you think about, you have an electrical conductor and you have a loss because of resistance and electrons encounter by colliding with the lattice of a conductor. In the same way, you have loss of light when light is propagating in a medium. And the three main intrinsic factors which contribute to the loss of light in a medium are infrared absorption, which we attribute as molecular absorption. Then at the short wavelength, you have electronic absorption because of the band gap, electronic band gap, and in between the molecular absorption and in the infrared and the short wavelength absorption in the visible near ultraviolet, you also have Rayleigh scattering because of the microscopic density and temperature fluctuation in the material. So these are defined by this these three equations here. So you got infrared absorption. So please note within the exponential there's a negative sign. That's why this curve here has a different slope than the rising curve for the ultraviolet absorption. So this graph here compares the electronic absorption at the short wavelength, infrared absorption at the molecular and infrared absorption at the long wavelength, and in between Rayleigh scattering. So the origin of molecular absorption is basically bond vibration. And as we know, bond vibrations are very complex. You could start estimating the cutoff edges by assuming that you have a linear harmonic oscillator, for example, silicon in the center, which is tied with 2 oxygen. And this model is, this linear harmonic oscillator has a linear motion basically. And that can be expressed in terms of fundamental frequency equal to 1/2 pi square root of force over reduced mass. It's just like a pendulum equation, basically, if you think about your pre-university physics. But this reduced mass part is quite interesting because M1 and M2 represent the cation and anionic mass. So as you increase the mass of the cations or anions, this frequency is going to change, which is why if you see, look at the silica, the infrared, the total transmission bandwidth is from, say, for example, 150 nanometers going down to just below 5 micrometer. Whereas fluoride glass have very extended, much larger extended transmission bandwidth. So if you change from fluoride, silicon to say sulfur, or silicon to germanium, and then you have sulfur, you can extend this bandwidth in the infrared. So in that case, you will see the transmission, ultraviolet transmission is sacrificed, but infrared transmission is increasing. So you can design glasses which are suitable for your purpose. So this is what, if you combine the 3 loss terms here, you can obtain this V-shaped curve. Okay, so you can see how silicates loss minimum is around 1.5 micrometer. And we use this window, low loss window, for optical communication system. So all your optical fibers are working around this window. If you go to larger molecular weight glasses such as tellurium oxide, which is made of tellurium as a cation and oxygen as an anion, you can make very good quality glass. We make here in Leeds. This will have a shifted infrared transmitted shifted window at around 3.5. If you go to chalcogenide, that will have around 10 micrometer. If you go to selenide and telluride, that will have 15 to 20 micrometer low loss window. But overall loss will also keep increasing because the way the Rayleigh scattering and electronic absorption works. So if you look at our atmosphere, this is the atmospheric window from visible down to 14 microns. So wherever you have these gray, lilac gray patch, these are the windows of high transmission. So here your solar radiation is coming in, then you have infrared, then you have, this is your atmospheric water here, which is increasing the loss, very important for maintaining the atmosphere. Then you have very high transmission in atmospheric window. For astronomy, this is a very useful window. So these are some very important windows. You can see what we can do. And these are the gases which absorb in this window. Okay, so you can see the transmission windows. Wherever you have these cusps, these correspond to absorption in the atmospheric window. So that's a very good example how things work in the mid-infrared. And later on we will see it. Very briefly, when you're designing optical fibers, you have to understand the critical angle at which you, Snell's law basically, you have to understand that and design core clad structure that helps to guide light. Okay, and you also have to design the core clad in such a way that majority of light is guiding into the core. Only tiny amounts of light will always leak into the cladding. So you can design either a single mode fiber, and this is the equation for the single mode fiber geometry. This is the shape of the Gaussian you will see, which is guiding through a single mode fiber. In multi-mode fibers, you will have more than one mode propagating. And that means whatever power you have launched into the fiber, that's going to split into several Gaussians. So the energy across the fiber cross section is distributed. So you won't have just one signal propagating, many more signal, and they will keep interacting with each other. So dispersion will be very high. And that's not really ideal when you want to do high quality signal processing. They are useful, multimode fibers are very useful, but for data analysis, etc., for imaging, it may be suitable to have a large modal area fiber, whereas for signal processing, for high quality data analysis, it's better to have good signal coming back to you. For example, in optical comps, we never use multi-mode fiber. We predominantly use single mode fibers to preserving the modal distribution. Okay, so we draw fibers. You have a, say, silica ampule, and you make glass in there. Say, for example, this is for making germanium sulfide, germanium tellurium selenide glass, which we made. We process in extremely pure condition, because you really need to avoid moisture, any impurities. They will contribute to to absorption in the fiber. So you use that, and then you make the core glass, you extrude the core, you draw the rod out, and then you make a cladding and you put them together and then draw them again to make fiber. Okay. So this is an example of how we draw fibers, mid-infrared fibers. And you can see here, the moment you draw fiber, you can see the water absorption peak. This is the harmonic of OH in the fiber, giving about 8 dB per meter loss. So for this, these are not very good for optical communication, but they are very good for sensing and light amplification. So here is an example of triple core fiber. You can see 2 cores are much nicer than the 3rd core because there's more than one mode guiding into it. So that's how, if you have a single core fiber, that's how it would look. A triple core fiber would, or quadruple core fiber would look like. There are 4 different guided areas. So once we make fiber, we can use for sensing. So this is basically an FTIR, and this is the germanium, tellurium, selenium sulfide, chalcogenide fiber, which has a very low intrinsic loss. As if you had no impurities, this would be the loss, and this is very, very small loss theoretically possible. But when you make fiber, we see quite a lot of lossy peaks. So this is OH peak, that's the carbon dioxide, selenium hydrogen, very small OH, side bands, free water. So wherever you have low loss, so for example, here you have loss in dB per meter. So if you have low loss, so between 3 and 4 micron or 4.5 micron, you can use that window. You can use this window, but where you have sharp peak, you cannot use because loss will take over. So we use this principle, and then we use the leaky mode, which I talked a little while ago, that some light will always leak into the cladding layer. And we use that principle. So what we did, we drew fiber and we attached this fiber into FTIR, and we start analyzing various types of liquids, suspended media, etc. And these are very well established sensing equations which for data analysis. And we published this article in Sensors and Actuators in 2014. And then we start analyzing various known liquids. For example, ethanol, we analyzed it. We analyzed ethanol together with methanol. As you know, methanol mixing is very problematic with ethanol, and you can see subtle differences. It is these subtle differences which is where your chemical analysis is going to be very valuable. Then you can look at how by changing the concentration, you can see the changes in the spectrum. And these are, again, very useful for calibration. So you can use this part of the spectroscopy range for quantitative chemical analysis. And just to give you an example, for ethanol and methanol, we did that. We did for vitamins. So you can see vitamin E, vitamin D, and comparing that with lemon juice against orange juice. And you basically now you are in the regime of data analytics. And you really need lots of data. So you have a measurement tool, which is optical fiber integrated with a spectrometer. And then you have analytes like vitamins, methanol, ethanol, and you analyze them. And then you have lots of data, you process them and create an intelligent system so that the system recognizes what chemicals it is looking for. So basically, you create a data bibliography in the system. That's how data analytics starts working for you. It doesn't work if you have just small sets of data. Very, very important point to recognize. So now I'm going to give you one good example of why we are interested in ulcerative colitis. Basically, it's an inflammatory bowel disease, which is the first indication for the onset of potential risk for cancer, bowel cancer, okay, or bowel-related inflammatory diseases. So it could be also related with Crohn's, it could be bowel cancer, it could be polyps which turn into cancer. But you may say, why you are doing this using optical fiber? Why can't we do X-ray, CT scan, or MRI scan? Well, there are clear limitations because X-ray, CT scan, and MRI scan will only see those cancers which are pretty advanced. Means patient may be incurable. Maybe you are at a critical stage, and that's too late. So what you need is early diagnosis. So for example, the way the bowel scanning occurs in many parts of the world, patient is given medication and bowel is completely empty, and then endoscopy is performed. And the endoscopy is usually patient is sedated for between half an hour to an hour. Now you think a patient comes to hospital, endoscopy is performed. During endoscopy, biopsies are collected, and that's sent to histopathological analysis. So you don't know for 3 to 4, 5, 6 weeks what is going on with you. And if there is a cancer, it could be potentially too late. Okay, so this is very important. And that's where, if you have spectroscopic technique in theater, during the day visit, you can give information to the patient by analyzing the tissue there and then, and say, yes, you need medication. Yes, you are critically ill and we have to do this step. And say, yes, you are not at risk at all. So this information is vital for patient benefit. And this you have to really, this is where engineering is very important. So we work with St. James's Hospital here. I've published some work. More work will be published later on. Continue to do this analysis work. So what we looked at is, first of all, if you're going to take huge endoscope cable and you're going to have an optical fiber there, so I explained you why then you need to choose a transmission window whereby you can obtain signal. And now I'm going to explain you how does body react to light. So if you all have your mobile phone, you switch on your torch and you put your finger on against the torch, you will see your finger looks more red because blood vessels are scattering light, and that's what you're seeing. If you had an infrared detector, you can get an infrared image of the fingertip, okay? And you could see the morphology of the finger as well. So any lesion, any kind of wound or tissue growth, you may be able to see. Any kind of textural changes you may be able to see. Because if you have a laser is a polarized light. White light is not polarized. But if you have a polarizer at the detector end, you can see the variation in the intensity. That's very useful. And here is an example. This is the scattering property of mouse's ear. Now, mouse is a mammal. Their skin texture or tissue texture very similar to our human beings. And you can't just go in the hospital and grab a patient and say, well, I'm going to do skin spectroscopy on you. No, you cannot do that because it's against the ethical rule. So we use animal models, and this is basically absorption part, you can see, and that's the scattering part. So like we discussed the low loss transmission window for optical fiber, we need to look at where is the low loss transmission window for tissues. So for example, between below 1100 to 800, you have very nice transmission window. And these are in 1/millimeter. So these are millimeter inverse. So when you say 0.1 millimeter, means you can go up to a centimeter and scan. If you had light in this wavelength, you can scan up to a centimeter. That's quite thick. So you can see lots of things from that. That's the beauty. First thing I would like to say to you, think about biophotonics that way. And that way, but this is just one good example. Every tissue in the body has a different scattering characteristics. So it's important to characterize that tissue. Okay. At longer wavelength, you can see higher transmission, at longer wavelength, you have a much poorer transmission. Okay, so the best transmission window for human tissue is in the visible near infrared, and this is an area where we are working currently. So you can see here what an endoscopist will do if some endoscopist is asked to analyze cancer. They will put an indigo dye and then go with a scope and look at the bowel. By putting different kinds of ink, you change the scattering properties, and they basically use white light and look at features. So he or she would look for inflammation, so you can see the blood. So that's basically inflammatory tissue. There's a big tumor here, okay, quite obvious, but this will not appear in the CT scan or MRI. These are polyps, okay. So this is a healthy bowel, so you can see very nice blood vessels, etc. So this is how people, when a patient goes, that's how it's examined. Cost, if you look at for ulcerative colitis, is staggering, very, very high. So early intervention. So why do we do early intervention? Because if you can treat it, then the cost of treatment is less, the patient is suffering less, and you have a healthy society. Think about that. A healthy society is more productive society. Okay. So a histopathologist a pathologist will look at in the microscope, and this is a huge amount of experience in pathologist's skill, which is your basically database. And he or she will say, well, this is cancer, this is not cancer. Sometimes they make mistake. There is no quantification. There is no molecular description. It's just visual optical examination, which is why we want to bring spectroscopy and imaging together. Okay, so for example, you look at, this is an ulcerative colon, and this is a normal colon. So difference. So what are we looking for? What is the gold standard? How do we compare? So in medicine, you always have to define a gold standard. So if you're bringing a new procedure, you have to have that procedure compared with what is the standard of care. Okay, that's quite important. So now I'm going to go into the details of what people do. So we are looking for basically biomolecules. So we will be looking for a very complex choline compounds. We could be looking for blood glucose. We could be looking for oxyhemoglobin, deoxyhemoglobin, etc., etc. So you name it. And basically, I'm going to go through quickly. So we had 60 tissue samples from colon from patients, and the tissue samples were collected where the inflammation is, and then slightly away from where inflammation was not present. So you compare that. This is very important, because if you go and take tissue sample far away from that, you're not making a good comparison. So when we take tissue sample, we freeze it at minus 80 degrees centigrade. All the metabolic processes stop. So when you take it out again, you can then quickly analyze and put it back if you want to do. But once all the metabolites have gone, then you cannot do spectroscopic analysis. You can only do imaging analysis. So that's what exactly we did with Raman spectroscopy. We used Raman scope and analyzed these samples using 514 nanometer laser. Very low power. We used typically 5 milliwatts, but we analyzed all the samples. So when you get the data, you often tissue samples fluoresce, and you have to correct that. Once you process the Raman data, that's how it looks like. And then you start analyzing the data. So lots of data were analyzed. And if you look at, this is something else. So this is an inflamed bowel data, right? So you have from 500 wave numbers to 3000 wave numbers, okay? And you have here ischemic neuronal cells. And you look at, start comparing what's going on. When you say ischemic neuronal cells, they are also suffering from some kind of inflammatory condition before the cells start dying and will be completely dead. So this is what we found, that there was quite a lot of similarities, especially in the large wave number bands and the mid wave number bands. So we start analyzing them and we start comparing. So phospholipids were one of the common things we found between neuronal cells and the bowel cells. And then we start analyzing, just focus on bowel cells. How do the bowel cells and bowel cancer look like? And somebody had done very good job of plotting different kinds of data from Raman data from different types of cancer. So you had lung cancer tissue data, you had breast cancer tissue data, cancerous tissue, all kinds of cytokines were there, and they plotted it. It was very, very helpful. And what we found from our own analysis, that you had these what we call antioxidants coming out quite strongly compared to what is happening in the healthy cells. So the black curve is for the healthy tissue, and the red ones are for inflamed tissue. So we are mucosally healed black, and inflamed is red. Okay. So what we are looking for. So we produced a list compared with what was available in the data. So striking examples of carotenoid were upregulated. Now, carotenoid is similar to what we see in carotene, which is carrots, tomatoes. And these are antioxidant vegetables. So what you're saying, the body is producing antioxidant to fight oxidative stress. Now, another very powerful heme group metabolite is myoglobin. And I know myoglobin and troponin are also present when a person is likely to have a heart attack. So 2-3 days before a major incident is going to happen, this is present in the blood. And that's what some of the people have reported, that if you could detect myoglobin and troponin in blood in potential heart patients, you can really save lives and save them from stroke-related disorder. So this is again connected with stress level in the myocardial tissues, which is why myoglobins come out. But myoglobin is also present in the bowel tissue. Okay, and that's quite interesting because it's heavily vascularized bowel. For most obvious reason is motion, and it's quite fibrous. So there are some very common important features. So you also see phospholipids, triglycerides. So this is basically all these things are trying to fight inflammation and providing signals to the central nervous system that, come on, yes, this is the area where we need help. Okay. So once you identify, then you start doing serious data analysis. So my colleague, Dr. Venkat Subramaniam, not only a very, very eminent endoscopist, he is prolific in data analysis. He really sorted this out. This was beyond me. And he analyzed all these 60 sets of data, compared them, and then presented in the useful format for much deeper statistical analysis using multivariate statistical analysis. So these are all his invaluable contribution. And then present it. So now you're presenting the data to the clinician, how to take decision and what's the confidence level. So these lots of data helped us to increase the confidence level up to 95%. If you don't have 90+% confidence, techniques cannot be accepted in clinic. This is very important point I would say about data analysis. So that's why not only the instrumentation is important, measurement systems are very important, data analysis is very important. So with that, I would conclude how we can take fiber optics into clinic and what it can provide, what are the technologies, challenges, etc. And these are some very interesting things where I do say there isn't much work going on in India at the research level. I don't see many papers in this area. So in terms of recommendation, I would definitely say laboratories like CMET, IITs should focus on infrared fiber technology. If you want to create a digital platform, this is something which country needs to think seriously. Thank you.
Thank you, Professor Animesh Jha, for this wonderful lecture. The forum is now open for discussion. There is one question as there in the chat box by Dr. S.N. Poti. For sensing applications, whether diameter of the optical fiber has any effect?
Yes, as I said, depends what you want to do. If you want to do sensing of very sensitive material, which is in extremely small concentration, diameter is very important. Is the surface of the sensitive area is also very important. So for example, let me go back. I can't exit. So here, this fiber was about 200 micrometers, and we stripped the cladding. We had only core of 3 centimeter long, because we were trying to detect the differences in acetic acid, propionic acid, then you had vitamin C's, different types of vitamin C's, particularly looking at children's food product, which could be suffering from adulteration process. If you want to analyze, say, for example, poison, you need very high sensitivity. And it's better than to do with single mode fiber rather than multi-mode fiber, which means you need a very thin fiber. Hope this answers.
Hello.
Okay.
Any more questions? So I request Dr. V. Kumar to invite Professor Animesh Jha and Professor Pakiri Sami for our panel discussion.
Good evening, Professor Animesh Jha and Professor Pakiri Swami. After the next lecture by Professor Pakiri Swami, we are planning a panel discussion, a very short and crisp discussion on the deliberations of this conference for the last 3-4 days, and how best the research activities taking place at various institutions across the globe could be synergized with our activities at CMET, so that our aim of achieving Atmanirbharta in our electronic components, especially on sensors, could be realized. So experts like experienced researchers like you, we would like to hear your expert comments and recommendations so that we can take it up with our colleagues and higher ups at the ministry and chart out a very definite path in the coming days. So I would like to request Professor Animesh Jha as well as Professor Pakiri Sami to continue in the same session where we would have the discussion immediately after the lecture by Professor Pakiri Sami. Thank you so much. Thank you so much.
Thank you. Thank you, Professor Animesh Jha, for this wonderful lecture. So, sir, you can exit from the presentation mode, sir. So we will move on to our next speaker, Professor M. Pakiri Sami, a strong promoter of innovation in Canada in the area of biomicrosystems. And he is also a professor and Concordia Research Chair on Optical Biomicrosystem at Concordia University as the Director of Micro Nano Biointegration Center and Optical Biomicrosystems Lab. He is leading the research on nano-integrated microsystems for cancer diagnosis to green energy harvesting, lab-on-chip biomicrosystems and micro-nano integration. He is a recipient of member Royal Society of Canada College, Fellow National Academy of Inventors, Fellow Indian National Academy of Engineering, Fellow Engineering Institute of Canada, Fellow Canadian Academy of Engineering, and many more. He published around 450 articles in journals and conference proceedings and published textbooks on MEMS, engineering and science perspectives, and 5 book chapters. He has received many grants to a tune of $16 million grants. So thank you very much, sir, for accepting our invitation.
Thank you. Can you hear me?
Yes, sir.
Thank you. Thank you so much for the nice introduction, Seema. Thank you so much. And it's nice to be in this conference, and a lot of good papers are going on. It's very nice. So are you ready to start the presentation? Can I?
Yes, yes. Please share your screen, sir.
Okay. Sorry. I was not ready. It says, it's nice from me or somebody else? Thank you. Good afternoon. My talk is going to be a micro-nano integrated systems and applications, including cancer diagnosis. And always I start with thanks to my students and all the people who have been part of my lab. So I'll start with basically, I'm working as a sensor person. I'm working on various types of sensing. So you all know that when you deal with optical sensing, especially in biological area, we have label-free and label approached. So we have lots of sensing like absorption, evanescence, SPR, and all that. So my lab is mostly focused on absorption, evanescence, waveguide based, and the LSPR, which is localized surface plasmon resonance. And we also do a lot of photonics integrated systems for biological applications. When you do that here, let me open my laser printer. So there are various ways that microfluidics is integrated separately from the photonics chip. We call hybrid integrations. Or microfluidics could be part of the same chip with photonics integration, so photonic circuits. So basically it's called monolithic integration. So we do both in our lab. So what are the materials we use here? As we use a silicon, glass, PDMS, and SUI, PMMA material platforms, depending upon the type of applications that we deal with. So I'll start with a good example of what type of different material platforms and how do they perform. So I'll do with comparison of different photonics integrated material platform with this idea of sensing growth hormones in milk. Growth hormones in milk is a serious issue. Countries do not allow it. Canada doesn't allow it, but some countries do allow it. So like US, they allow up to 100 nanogram per ml. So that's the maximum limit is allowed in the milk. But what is happening there, we don't know. So basically, there are a few companies approached me to develop sensors for detecting the growth hormones in milk. So what are the techniques that exist here? As you can see here, standard techniques that exist right now are like SPL, CL, CMS. These are all standard techniques that exist, but they're very expensive and takes a lot of time. So we want to do lab on a chip concept to detect growth hormones in this case to save time so that we can make handle devices. We can give it to all the farmers, and this could be detected where the milk is collected. This saves a lot of cost as well as a lot of time. And basically, the idea is to help the public a lot. So initially, we started with the simple antigen antibody interaction-based, fluorescent-based lab on a chip concept, as you see here. Then we moved to photonics integrated circuits in that case. So here we see for the fluorescence detections, we use a silica on silicon, basically it's a silica waveguide on a silicon platform. So silica on silicon with the PDMS as an integrated chip. You can see this central chip, which is optical or photonic chip, which is a silica waveguide on a silicon chip, while the microfluidics is on PDMS chip here in this case. why things doesn't move. Let me take out the laser printer so it's easier. Okay. So here, silicon with PDMS. So PDMS is used because it's good for microfluidics. Silicon is good for dealing with optical waves and basically in the infrared as well as in the optical region. So you can see here, this is a waveguide chip. This is a silica waveguide, and we can see that microfluidics here. And this is an integrated chip with the silica waveguides in a PDMS microfluidic chip. These are inlets and outlets for microfluidics to flow. And this is being tested now. You can see very clearly the waveguide of silica here. And we did the testing with the different growth hormones. And we can see here the detection limit here was almost around 240 nanogram per milliliter, which is higher than what is specific, which is generally accepted. Okay. So then we use a quantum dot instead of fluorescence. We went to the quantum dot and to improve the performance. Then we got improved with the quantum dot performance. Then we have moved to localized surface plasmon resonance. So what happens here in surface plasmon resonance is we need to integrate nanoparticles, basically gold, or in this case, we use the gold nanoparticles with a microfluidic setup. So you can see here, this is a microfluidic platform, and when integrate gold nanoparticle, and we can do all the biological protocols, immobilize them for diagnosis of different biological elements. In this case, is a growth hormones here. This is the protocol we developed. And you can see here, how do we do that? As this is optical waveguide through which the light is propagating, and you can decorate it with many nanoparticles here. As you see nanoparticles here, this is one nanoparticle here. So that you can decorate with multiple nanoparticles, and you can augment the efficiency of optical coupling in this case. So you can see some of the modeling we show you here. Depending upon the size of these nanoparticles and the intensity, you can change the coupling between the outside of the waveguide into the waveguide. We have evanescence coupling, we call it. So how will we integrate these nanoparticles on these waveguides? There are two ways we do. One is the in situ synthesis, other one is ex situ synthesis. In the case of in situ synthesis, the gold precursors and the reducing agents to make synthesized gold are passed into the microfluidic channels, and they are basically reduced inside. Or other way, ex situ synthesis, we can make the gold nanoparticle outside, and then you can absorb it onto the microfluidics inside from outside. So this is what happens. So in ex situ, we make the gold nanoparticle. In this case, for example, it is a simple reduced method of gold precursor, and we can do the self-assembly on any substrate like this one here. Okay, this is all angled convective assembly is what mainly used. So the nanoparticles are produced, and then you can decorate them on the PDMS, or you can use any microfluidic platform for sensing. So these particles could be a nanostar, nanorods, or nanospheres. Any of these isotropic and anisotropic nanoparticles could be done. So you can see that here as in ex situ, your gold nanoparticle, which is made outside, and then you integrate them inside this lab on a chip or microfluidics. Or you can use the precursor and made to react with this microfluidic chip with this polymer, and then you can in situ synthesize gold nanoparticles. So both ways are possible, like the one that you see here. So once you have these gold nanoparticles integrated onto the microfluidic chip, then you can also do the thermal treatment to change the size, basically because the morphology of these gold nanostructures, as well as the distribution of them here, as we see in this case. So which is also by which you can also change the sensitivity of the chip. So we use a lot of PDMS for microfluidic chips because for various obvious reasons, they are good, biocompatible, and they are very easy to handle for microfluidics. So in the case of ex situ integrations of nanoparticles, you can see the nano islands, we call them because they're larger and they're clustered. So we call them a nano islands on PDMS microfluidic chips. They're basically called ex situ integrations. So if you look at the LSPR, the localized surface plasmonic resonance, that's what you see here. And depending upon the size, you will see the shift in the peak, LSPR peak of this, which is what is indication. So anything happens on the outside of this nanoparticle, which is the environment of nanoparticle, which will change the LSPR shift. That's what we will be measuring here. Okay. So to detect the growth hormones, we came up with this protocols, as you see here. So we have nanoparticles integrated on microfluidic chips, and we follow the various bioprotocols. And then finally, we can detect growth hormones here. So whenever for each step, you see the shift in the plasmonic here, peak wavelength, that's we call the plasmonic shift. You can see, here, the plasmonic shift changes with time. Basically, that also changes with concentration of these growth hormones, from which you can find out the concentration of the growth hormones. So here you can see there's a microfluidic glass microfluidic chip integrated with Ex-situ integrated with nano islands, and you make a microfluidic chips on top of it with the PDMS. As you see here, this is a gold nano island. The red color, that the pinkish color you see is a gold nano island. And you can see the shift in the wavelength, which is the plasmonic shift with the concentration of the growth hormones here. So then we started integrating nano features, and as we see here, this is a basically evanescent based sensing. You can see the nano. This is basically optical waveguides, and you can decorate these waveguides outside with the gold nano islands. That's what's called nano enhanced evanescence technique we call. As you see here, there's an optical waveguide decorated with nanoparticles on everywhere on the side. By doing this, we can increase that evanescence coupling, by which you can also see that you can increase the sensing to 20 nanogram per ml. We could do that. Okay. So one of the things I want to talk to you about here is, it's called cascade waveguide coupler. So this is multiple waveguides. You can see the light comes in through the waveguide and split into multiple times. And then there's a microfluidic chip at the center. We don't see that here, through which the fluids are flowing through, and by which you detect them. So you basically sensing areas there. So you sense the growth hormones, and the light is being coupled here, and then you measure what happens to the basically the whatever lights that couples by fluorescence coupled to the evanescent coupling to the waveguide. This is what happens here. So you can see some of the close look up at the waveguides and how their circuits are, and how the light is being coupled into the waveguides. And you can see the testing methods here, the test setup, that what you see here, and finally the test has been done. So you can see here, the detection limit in this case is up to almost 25 nanogram per ml. So if you use only one waveguide, as the case with the single waveguide, as this case here, you're talking about 240 nanogram per ml, which has been reduced to 25 nanogram per ml, which is that highest 10 times improvement in sensitivity by having cascade waveguide coupler. Then we went from ex-situ to in-situ synthesis based localized surface plasmonic resonance. So here basically we do microfluidics plus microphotonics plus integrate nanoparticles for bioapplication. So here we can use silver or gold. We use both nanoparticles in this case. So this is a microfluidic chip. You can see here we produce this nanoparticle by in-situ synthesis. That means there's basically the precursor is used to react with this PDMS cross-linking agent. So the reduction of precursor happens inside under high elevated condition like temperature or microwave. Then you can basically produce nanoparticles on PDMS. So it's basically, that's called in-situ integrated PDMS in this case. Sorry, in the in-situ integrated PDMS chip. So you can see that this is a PDMS chip in which gold particle has been decorated by in-situ way for sensing. So you can see by changing the temperature, basically you need to heat treat them, and by changing the temperature and time, one can change the morphology of these nanoparticles. This is very important because the size of this nanoparticle is very critical depending upon the size of the bioparticle that you are going to detect. Okay, if you are detecting larger particle like the growth hormones, so growth hormone pretty large biomolecules, to detect these larger molecules, it's important to have a larger nano island, so like the one that you see here. So we can tune this morphology of this nanoparticle based on the size of the biomolecule that you plan to detect. And you can see depending upon the time, like if you anneal for 48 hours or 18 hours, you can see the change in the size of these nanoparticles in this case. So you can see here, you can by changing the absorption, basically the plasmonic shift, you can see that here with the time of annealing as well as the agent that you use for reducing with ethanol or just water, you can change the size of these nanoparticles. Okay, and you can see this is a microfluidic chip that you see at the center, and you can see the red color that indicates the nanoparticles in situ synthesized in the microfluidic chip. So that's basically the sensing area for us. And if you look at the LSPR shift of these, basically the nanoparticle, you can see that absorption peak is shifting depending upon the size of the nanoparticle as well as the intensity of the nanoparticles. So that's a beautiful picture of a microfluidic chip. And you can see the microfluidic chips on the surface of the microfluidic chips are decorated with the nanoparticles here, which is basically in situ synthesized, as you see in this case. As you can typically around 50 nanometer size particles here, around 120, but you can see some of the sizes are around 100 size, less than 100. 60 is the typical size that we got. Okay, so sorry, and how to do. We also did synthesis in a microreactor for gold nanoparticle synthesis in microfluidic chamber. So generally, if you buy a nanoparticle in a colloidal solution, there's a 30% change, 30% variations in the size distribution of this nanoparticle. So if you want to reduce the size distribution, variation, then what you can do, we can have a very close to controlled environment for synthesis. So that's what we do in a microfluidic chip. So here, there's a microfluidic chamber, and you pass gold precursor and reducing agents inside. And you can see that as the both of them flow, of course, in microfluidic chips, the fluids don't mix. They only mix at the boundaries here, at the center. That's what you see here is when the two fluids flow inside the microfluidic chamber, where they mix on the boundary between these two flows, where the synthesis happens. Otherwise, synthesis doesn't happen. So unless you use a 3D mixer or something like that, you cannot have a uniform synthesis. But then we use the 3D mixture, and there's micro mixtures that we developed, which is then we get a uniform mixing of those precursor and the reducing agents inside this microfluidic channel, and we can get a very good high output throughput of synthesis that we could get with this. Okay, so in this case of in situ synthesis, as you see here, this red color indicates that gold nanoparticles synthesized on the PDMS microfluidic chips. So there are basically nano islands embedded on the microfluidic chips, like the one that, like the one you see here. So that's a microfluidic chips, and everywhere you have the gold particles embedded onto the surface. Now, each island will act as a platform to absorb bioparticles, whatever you want to detect. So in this case, it's a growth hormone. So that's what we are trying to do. Then we can detect the LSPR, then we can do the LSPR shift depending upon the concentration of this growth hormones, and we did the LSPR shift has been detected. And you can see here, we can go up to 4 nanogram per ml by doing this. So in situ integration of nanoparticles inside microfluidic chip can give up to 4 nanogram per ml in this case. So that's just something very, very important, very good results for us. Okay, so we got 8.3 times improvement in size uniformity because we nanoparticle synthesized in the micro scale. So you can see this is a more detail of that, what happens to inside the microfluidic chips. So we have nano island and integrated onto the microfluidic chips and various bioprotocol. These green ones are basically the growth hormones. So basically we change the shift in this plasmonic shift as different steps in the bioprotocols. And finally, when the growth hormones get attached to it, then you have the final shift, and that's what gives the 3.7 nanogram per ml reduction limits. Then we did the same thing. Instead of gold, we also tried to do with the silver PDMS Nano Composite. So we tried to reduce the silver nanoparticles by silver precursor into this PDMS using the curing agent as a reducing agent. And we saw a lot of the silver nanoparticles in situ synthesize. So we have here microfluidic chips, and we have central wall with the nanoparticles on top of integrated on it. So the light is basically fiber got integrated with the microfluidic chip. So light is coming through this input fiber and being collected to output fiber. But here is what the biosensing that happens within this wall. Okay, as we see here. Okay, so we can basically here we have this wall here, we can see is coated with a lot of nanoparticles, and the biosensing protocol happens. As the growth hormones get immobilized onto this wall, then you can sense, you can measure whatever that we wanted to measure. So we can see the LSPR shift that is being measured in this case is it's, depending upon the different, of course, size of these particles, but we get a very good sensing in this case. Okay, so so summary here, we use a different technique for detecting these growth hormones here. From simple fluorescence to evanescence with a waveguide, single waveguide, it got 240 nanogram per ml. Then we did LSPR. And when you do the cascade waveguide, we got 25 that I told you. So we have 10 times. So this is about evanescence coupling. So evanescence is definitely works very well. But when you do LSPR techniques, we got around 3.5 to 5 nanogram per ml, which is highest sensitivity that we got with LSPR. Okay. So definitely LSPR is, it works well for us. So we can see from single waveguide to multiple waveguide to LSPR, there's a big improvement in sensitivity, or the detection limit has gone from hundreds of nanogram per ml to few nanograms per ml in this case. So definitely LSPR is a better technique in this case compared to other technique. Okay, so this is one of the nice papers that we have. Basically, this is a photospectrometer that you see all the time. So we miniaturize this entire chip of this into a tiny integrated lab on a chip. Okay, so what happens in a lab on a chip here is that's what happens. You have microfluidic channels, and through which you pass any bioanalytes. Then there's optical input waveguides, which collects the information. The light goes from this waveguide, collects information of the sensing particles, then goes to the output waveguides, diffracts into the grating in this case. So we have a shell grating in this concave grating here integrated into it. And basically, depending upon the multiple analytes, multiple analyte detections or different detections, so you can get a multiple wavelength signals which are detected in this case. So this is the whole microfluidic and the photonic circuits all integrated in the same chip. This is called monolithic integration. As you see, this is a chip that what we produce on silica on silicon waveguide. You can see this input waveguide, light comes here, and there's a microfluidic channels here. So the fluid flows through this, and that's a inspection or sensing zone here. The light gets coupled by output waveguides and goes us through the grating. This is what you see here as a grating here, and lights get diffracts on basically on the shines on the grating and diffracts into multiple output waveguides. So you can see there's a lots of, so you can go up to 200 analytes one can detect with this. It's a very tiny chip from 1.6 centimeter by around 2.5 centimeter size chip. And that's a chip as now basically essentially this chip will replace this entire micro. So this chip can be put into any handheld device. So we can have a handheld device with multiple spectrum analyzer. So this is something interesting thing that we did. And also we developed this MTNS in nanoparticle integrated chips for various other applications like aerospace and ice melting applications and de-icing, generally we call heating applications, and electromagnetic shielding applications, or various applications are being developed with this. Okay, so that's, you can see very closely here, this is nanoparticle embedded onto this PDMS surface. That's in situ synthesize. Then other type of integrations we did is, instead of having the microfluidics in a static chip, we want to have a microfluidics inside the microcantilever. So this is, we call the suspended microfluidics. So we developed this suspended microfluidics out of a PDMS. So this is a polymer cantilever. Inside that we have a microfluidic that flows through. Now these microfluidics can be in situ synthesized with the gold nanoparticles. So we can see this red color indicates gold nanoparticles integrated microfluidic chips. Now any biological sample detection that you want to do, the detection area is this. So as the interaction happens between analyte and antigen or antibody or any analyte here, then it undergoes a stress which will basically deflect this cantilever. So basically the deflection of the cantilever will indicate the intensity of the bio interaction that happens inside this channel. So that's a whole idea of this sensor in this case. So we can see here inside this microfluidic channel of this is the microcantilever. So whatever you see outside is a microcantilever. On the inside, that what you see is microfluidic channels and decorated with nanoparticles all around, as you see in this case. So as the flow happens through these microfluids, so the bio interactions will happen with the nanoparticles all around, which will change the stressing distributions on the cantilever, which will in turn try to move the cantilever. So as you see here, beautifully here, as that antigen-antibody interaction happens inside the cantilever, it's in the microfluidics, it tend to produce a stress. As a result, that microcantilever will tend to deflect. So we measured basically the tip deflection by here, basically the light lever techniques, and that's what we used in this case. So you can see here by measuring the deflection of the cantilever with the different concentration of the growth hormones, we even went up to 2 nanogram per ml, which is the lowest that we got so far, by using the mechanical setup here, which is basically interaction. I wouldn't call it pure mechanical. It's a biomechanical interactions in this case. So okay, so one can detect basically the smallest concentration in this case with this microcantilever integrated with microfluidics, integrated with nanoparticles. So another example that I want to talk about is early cancer diagnosis, how we did that in the recent times. So this is some of our interesting work for us. And here, what we do is, as we see, we have been hearing a lot about cancers and biological things today. And here in Canada, we expect 1 in 2 to get cancer and 1 in 4 to die. This is what in the lifetime of Canadians. This is very scary number. So what we wanted to do is very early diagnosis. So what we mean by early diagnosis here is we don't want to, so before, say, if you look at the different stages of a cancer, we wanted to go do something from the stage 0 if something is possible. So one of the things that we used to do that is exosomes, we call, or microcellular vesicles, exosome or extracellular vesicles. This is what we are going to use. If you look at the typical way of cancer detections presently we have, we can only do it at very later stage of the development of the cancer. Or if people have started, a lot of work is being done in circulating tumor cells in the blood flow, which also can be used to detect the onset of cancer, which is still not very early. So other thing that what we're planning to do is microvesicles or exosomes. This is what we are going to use so that we can do very early diagnosis of cancer. Okay, so what is this exosomes or microvesicles in this case? So I'll just use mixing the term exosome microvesicle. Of course, there's a lot of debate is still going on, is being settled, but let's use exosomes for this case. In our case, okay. So these exosomes are generally around 100 nanometer size particles, like virus particles, is bilipid membrane particles, which has inside a lot of biological informations like DNA, mRNA, miRNA. There's a lot of proteins and everything's part of it. So these are basically the particle shells shed by cells. Basically, these particles are used for intercellular communication. So this is basically the communication tool between cells. That's why the cancer propagates from one place to other place. So they're very important. Before these extracellular vesicles or exosomes get into this bloodstream, once they get into the bloodstream somewhere, then it can go to any places and start the cancer there. So idea here is these vesicles all the time shed by all the cells, not only cancer cells, even healthy cells. Every cell sheds this. Okay, so there's a good exosomes and bad exosomes. Bad exosomes mean is shed by the cancer cells. So is it possible to identify those cancer exosomes and then detect them so that we can do very, very early cancer diagnosis? This is the whole idea of this. Okay, this could be done by any body fluids, not even blood, it can be any body fluids. Okay, people are using even saliva and urine, and many of these could be used for. So eventually we can go to the liquid biopsy techniques, no invasive way of doing it. So that's where a lot of work is being done in my lab right now, as liquid biopsy based techniques using these exosomes for very early cancer detections. So one example, let's talk about a few things that we did. So this is basically a microfluidic chips, as we talked about before, where Xe2 integrated nanoparticles. So, and it's basically you pass this exosomes and then try to detect. So by detecting using this LSPR, which is sulfase localized plasmonic resonance techniques, as I told you here. So in this one, let's see, you have a gold nano island, same way. So we detect this exosomes. Here we have exosomes here, as we see this pink color one, the exosomes. And the biomarker for that is basically we use the VN96 polypeptide. So this is what being used to capture those exosomes on this. And the VN96 has been mobilized on these nano islands with various bioprotocols, as you see in this case. Okay, so here what we did is, this is the concentration of the exosomes. Why we use a concentration of exosomes? You can see here the concentration of exosomes in the blood, for example. This was for breast cancer work. It goes around 14 billion particles per ml when a fully developed cancer, to around 0.3 billion per ml in the case of no cancer. So the concentration of the exosomes in blood, for example, can be indicator, simple indicator of the onset of a cancer in this case. So we are trying to develop a sensing platform which can sense from no cancer to fully developed cancer. This is what we see. So we try to measure the LSPR shift from completely no cancer to fully developed cancer. This is what the chips that we've been doing. So this is some of the microfluidic chips that we developed to detect this by using XC2 nano integrated techniques. And we got a very good results with this. Now, recently we got one paper published in Biosensor Bioelectronics, this one. And you can see here, this is a fully integrated microfluidic chip, which has a 3D micro mixtures here. You can see this part is a 3D micro mixture. So what we do is we use basically the blood, for example, purified, or we already cleaned blood here with exosomes, or you can say exosomes here. And then the biomarker corresponding to that as a VN96 with the magnetic particle. So here we use the magnetic nanoparticles, which are immobilized with VN96 on top of these magnetic particles. When this magnetic particle goes through this micromixture, as well as this antigen, which is in our case, exosomes goes through, they get mixed thoroughly. So by doing that, we can see this exosomes get immobilized onto the surface of these magnetic particles. So as these magnetic particles immobilize with these exosomes as well as this VN96, we can do all kinds of measurements. We can do optical measurements, we can do cytometry, we can do various measurements that could be done, which is done in this chamber. And we are doing the measurements here. After that, what we do is we try to collect this, whatever got immobilized. So we try to collect those magnetic particles precipitated here. So there is a sort of a sedimentation chamber that we have here. So here we collect those magnetic particles, and then the pure supernatant goes out like here. So we collect these magnetic particles, which are basically loaded with these exosomes. So basically this chip is used for encapsulation, for isolation of exosomes. This is basically identification, isolation of exosomes that happens here. So whatever that's magnetic particle loaded with exosomes are collected here, and then you basically protein SK, you pass it afterwards and isolate those exosomes from that for further analysis. So once you take these exosomes from this chip here, we can do all kind of, we did all the ddPCR analysis. We found out all the DNA analysis to find out what they are, whether they really, what kind of cancer they are. So it was, we know that it was basically breast cancer. So identify that's the breast cancer. So this technique could be used to identify by trapping those exosomes. Okay, this, and you can do multiple deductions here. Multi-cancer deductions is possible in this case. So this is a much closer look of the chip here. You can see here. And this is what happened. This is a magnetic nanoparticles, and you can see the pink outside is loaded with those exosomes. And this is what get collected in the sedimentation chamber at the end. Okay, and you can see some of these nice pictures here. You can see here, this is magnetic nanoparticles loaded with streptavidin and VN96 here. Then we have exosomes get collected on the top of it. Then we can remove the exosomes afterwards in this case. So this is after removing the exosomes for further analysis. So we have a chip that really works very well to identify, isolate, and exosomes, which can be used for very early diagnosis of cancer. So that's a kind of work that's happening here, and this has very good potential for liquid biopsy techniques, and you can see some of these exosomes here, and we can is atomic force microscopy of these exosomes that you see here from breast cancer in this case. Okay, and these are my group, and with that, thank you so much. I can take any questions if you have.
Yeah, and thank you, Professor, for this excellent presentation. And now the forum is open for discussion.
Professor, that was really wonderful. Thank you so much for elucidating technology. Just want to understand a few basic things, if you don't mind. In your LSPR device, I could see that, especially before you started talking about the cascading thing, the single portion, I could see that the deduction is taking place as a function of time. What really happens there, and then only it stabilizes. Initially, with the time, it goes up.
Yeah, that is this is a continuous flow that happens there. So we need to allow the incubation. So basically, there is a nanoparticle immobilized with all the biological markers on that. So they have to immobilize. So basically, it takes time for antigen-antibody interaction to take place. That's it. Because there's a continuous flow. If otherwise, if we don't have a flow, then we have a residence time. We just leave it for a few minutes so that the immobilization basically is complete.
During your antigen antibody, you have also, I understand, blocking layer. Can you throw a little bit more light on that?
Okay, the blocking layer is this is to block this basically the antibody not to stick on every surface. But we have microfluidics, and you want only on the nanoparticles. You don't want anywhere else. That's basically the blocking layer. Otherwise, the fluorescence, it's going to confusing results on it, because we're looking at LSPR shift. That means we want only the bioparticles sticking to only that gold nano island, not everywhere on the microfluidic platform.
And another very basic question. You said the LSPR resonance shifts the size of the gold nanoparticle.
Well, I said with the size of the nanoparticle, you get LSPR shift, because the size determines your basic LSPR peak resonance wavelength. So the larger the size is, it shifts towards the larger wavelength. Smaller the size, it shifts towards the smaller wavelength. So as we have any size, whatever the given size, we have the definite LSPR wavelength for the resonance wavelength. But as you do that biointeraction that happens on the environment, it changes the refractive index around this nanoparticle. As a result, you always see the redshift. You always goes toward the redshift, so that you get a higher wavelength. So the shift in the wavelength indicates the intensity of the biointeraction that happens on the surface of that nanoparticle.
So does this mean that for a given analyte, I need to optimize the gold size and then?
Yes, I didn't present it here, but what we did a study here is, let's say if you have so this is nanoparticles or around 100 nanometer, let's say, or 50 nanometer, right? So now, if you have a 10 nanometer nano island, definitely it's impossible to lock those larger nanoparticle onto the smaller nano island. So depending upon the size of the nanoparticle that you're looking at, it's important we size this depending on the size of the bioparticle that you want to capture it on the nano island, we need to tune the size of the nano island. That's what we realized it. So we optimized, basically, we have published a paper, I didn't have it here, but we published a paper on how to optimize the size of the nano island depending upon the size of the bioparticle. Look at it. So our growth hormones is a polypeptides, is a larger one. Okay, it's a larger molecule. So we need to go for a little larger nanoparticles in this case. So what we did is we created the nano island in this case. Yes, you are right. So if you want to detect a very smaller particle, then you need a smaller nano island. Is good enough.
Thank you. Thank you so much.
Yeah, welcome.
I have a question, Prof.
Please.
You showed some beautiful structures of multiple waveguide arrays. what's the level of crosstalks you have? If you're analyzing so many signals, do you have crosstalk?
Crosstalks, earlier also I did a lot of working on this telecommunication optical waveguides, but the crosstalk is a huge problem between. So what we need to do is I need to space the distance between the waveguides such a way that crosstalks. But in this case, there's no multiple signal was going through. It's a single signal everywhere. Okay, so it is evanescence coupling that happens on the surface of the waveguide. So I didn't have the problem of crosstalk in this case, but it will be a problem when you have multiple signals that coming in.
So you didn't have channel to channel signal overlap. That's one of the things I was interested in.
So here I want to just increase optical coupling in this area. So for me, simply it was more number of higher the optical area is, higher the optical coupling for me, as simple as that. But in the case of a real waveguide, then if you all these, let's say, independent waveguides, if you're talking about multiple analytes, these multiple analytes happens at this area. Let's say you collect all the signals here, all the wavelength are coming here, no problem. So whatever be the cross, all the wavelength are coming, finally all routed to the single waveguide here. So this single waveguide, which carries all the wavelength, okay? So now it is being diffracted into using this grating here, okay? So any crosstalk you talk about should happen only here and this detection waveguides here, which is the outlet of the grating. So, but these gratings have been designed for no crosstalks. That means the waveguide here have been spaced such a way that there's no crosstalk there, because this is basically, we have to at least minimum of 5 micron gap between these waveguides for basically silicon waveguide that we did. So to have not to have a crosstalks.
So one more question, sir. How do you clean the surfaces?
Oh, we have protocols developed where we use different cleaning agents, and
you have a multiple use.
Yeah, for multiple use. We tried for multiple uses, yes, this one's, yeah. And also we use this as a stamp to make the whole thing in a plastic also. We did it, I didn't have it here, but we did the whole thing in a plastic too. So we can put simple throwaway chip and where it has all the microfluidics, microphotonics and gratings all done in a single chip. Okay.
Thank you.
I have a question. How early is the detection possible by this technique?
How long it takes to detect, you mean in terms of time?
No, how early when you have a cancer?
Oh, you're talking about cancer.
Yeah.
You're talking about cancer.
The last part.
Yeah, okay. Say, that's where the famous curve I was showing you. Where is that? Here, this curve, yeah.
Right.
So this green indicates the 0.3 concentration.
Right.
It's almost no cancer there.
Right.
Absolutely, there's no cancer, right? So when you go to this around 50 times, then you have fully developed cancer. So basically, our sensor can do even from no cancer to full cancer.
Okay, that I understand.
Yeah, so we can cover the entire range. That was the idea here. But now we are doing a lot of work is being done right now. This little older work I'm showing you here. So here we also identify what is the quality of this exosomes now. We are doing a lot of work on that. So it's not only, so here we know there's known breast cancer. I know it's breast cancer exosome, so easy for me to detect. But if unknown cases comes, what kind of cancer it is? So we are looking into the content of these exosomes. Based on this makeup of these exosomes in terms of mRNA, we can also go into detecting what kind of cancer is getting into that. Because this is what we are doing more work now, including GBM to a lot of work. I'm doing more work on GBM nowadays, and various type of cancer also I'm doing. Yeah.
The question, second part of the question is, if you find there is a cancer or something like that, is there anything possible to inhibit that further?
To inhibit that further?
Yeah.
This is idea that I work now is that first of all, when you know that there is an onset of cancer is, first of all, the communication happens between the cells with these exosomes, right? Is there a way to cut the communication so that at least I'll slow down the process, okay?
Right.
Then now the lot of work is being done to use these good exosomes. There is also good exosomes, okay?
Right.
And you can load those good exosomes with various therapeutic medications, for example, and then you load. I recently read a nice paper on that as loading these exosomes with anti-cancerous materials.
Right.
Okay.
Yeah,
and then these particles are such a friendly bioparticles for cells, it can enter easily even through blood-brain barrier. So it gives a lot of scope in future as also as a highly therapeutic agents. It's not only a sensing therapeutic agents. I think there's a lot of research start happening in this area. I started working in this microfluidics using this, but now I see a strong interest. There's a lot of future in this. Yeah.
Brilliant. Thank you.
Thank you.
Just one more question in the chat box. That is from Mahesh. Are these chips for one-time use only? What will be the cost of these chips?
The cost of the chip is always depends on how many you want, right? This is like a computer chips, right? This is the multiplicity is the key. So if you are going to make a chip on silicon-based ones, you can do multiple times use. If you're going to use and make chip on PDMS or plastic base, maybe you can use it for a few times because it's very difficult to clean completely after a few number of uses. So in that case, the PDMS chips it's very throwaway price. I wouldn't even give it. You can make it in $1 or $2 chip, eventually. Okay, so it is not the cost is important here. It's cost of making is not a deal at all. It's other things what makes it more expensive. Legalities, and testings and FDA approval. These things are expensive. Chip is not at all expensive.
Thank you. Thank you for this excellent talk, and thank you for accepting our invitation.
Oh, you're welcome. Thank you so much. I can stop it.
Yes.
Thank you.
You can stop the screen sharing. So before we go for the panel discussion and future roadmap, I request Dr. Muralidharan to announce the result of best oral and poster presentation.
Good evening, everyone. The results are out, and thanks, jury, for giving us the results. The oral presentation first prize goes to OP6, presented by Ms. Rasha Rahman PK. And in the case of poster presentation, first prize goes to ES002, Dr. K. Girija. And second prize goes to ES005, Dr. Manju Pandey. So these are all the prize announcements, and hearty congratulations for all the winners. Thank you.
Certificates would be mailed to the winners by the organizers.
So now we will move on to the last part of this conference, that is first on the panel discussion and future roadmaps, then on the concluding session. So I invite the following panel members, that is Professor Animesh Jha, University of Leeds, Professor Pakiri Swami from the University of Concordia University, and then I call Dr. Pramod H. Bose, scientist of ARCI Hyderabad. Then I request Director General CMET, Dr. B.B. Kale, the Director CMET, Dr. N. Rigu, and the Chairman Technical Committee and Scientist G of CMET, Dr. V. Kumar, for the panel discussion.
Hello.
I request actually Dr. Seema and Dr. Radhika also to be available, please.
Yes, we are here only, sir.
Yeah,
so probably I can kickstart the discussion on this because we have had very interesting talks over the last couple of days, and experts from different institutes from various parts of the globe have talked to us on materials, improvement in materials design, improvements in device designs, prototype development, and just a couple of lectures back, we have seen a very matured product in the market, sensing lung cancer at a very, very early stage. Now, this is high time for us now to look back and see how best, especially At CMET, we would like to reach out to Indian diaspora experts like you and have your views and recommendations as to how we can gear up our research activity, establish a very interactive network among interested researchers across the globe, and see how best we all contribute towards achieving self-sufficiency in sensors, especially with IoT and Internet of Everything taking a very, very matured step in India. So with these few words, probably we can listen to recommendations from experts in this panel and also hear the views of our other panelists like DG CMET, Director CMET Trishur, and the two young women scientists of CMET who are actively engaged in very good research on sensors, Dr. Seema and Dr. Radhika. So with these few words, I would like to request others to, Dr. Kale probably could give a few introductory remarks and then we will catch up as the discussions evolve. Thank you. Dr. Kale, please.
Dr. Seema, has he joined?
Sir, he is in the panel. Yes, sir.
Yeah, he's there.
Dr. Kale?
Sir, then let him join. We can request Professor Animesh Jha to start, say, what is his views on.
I have to go in 10 minutes because I have another meeting at 1 o'clock and I need to prepare a few things for that. Very quickly, very, very nice talks. I could not spare much time, so was only there for last two talks. Very interesting presentation from Dr. Pakri Swami from Concordia. I think for me, if I was if I was responsible, I would put early cancer diagnosis, particularly looking at bowel cancer, breast cancer diagnosis, early smear test for women, and also look at, because India is a hot spot for bowel and stomach cancer. We have a big robotics program here, and a couple of my colleagues had a joint research program on that. And combining that with robotics will be very useful, particularly where invasiveness of the diagnosis is absolutely critical. If you can avoid invasiveness, much better. And I think some of the approaches which I heard today is may lead to, but have to collect samples. I think bigger question also for me is to management of sensors for the management of diabetes. And there has not been any low-cost breakthroughs there. It's still pricking with your finger with needles, collecting blood sample. It's not really high tech, sorry. So we really need to come up with some better ways of early diagnosis. And I think for Prof. Swami, I would say one thing which I know of, because I have a small CR UK funded project, 7 UK universities are involved. And that is, in breast cancer, is ductal carcinoma in situ is very, very difficult to diagnose. It happens in the milk canal where cancer starts growing. And because CT and MRI cannot detect it, it advances and starts spreading into lymphoids, and then it's irreversible. So that's another very big challenge. And we are seriously looking at here, because in UK we have about 400,000 patients for breast cancer.
Thank you, Professor Nimesh Jha. Probably Dr. Bib Kale, are you now available?
Yes, can you hear me?
Yeah, please continue.
So thanks Animesh for giving us time for this panel discussion as well as other members. The purpose of our sensor conference was to we can have the collaboration with the other international or the other universities and industries, because we have IoT center of excellence, and the center of excellence needs to be self-sustainable after 5 years or 6 years, and that's why the commercialization of sensor is very important. So both the research research on the materials of the sensors, their fabrications, and other variety of new sensors has to be is very important for the country. So this conference was really I should thank I should thank the research director Dr. Seema and team. They have done a wonderful job, and we could hear many new things in these lectures. So many other participants, so many other speakers have given the idea of biosensors and other optical sensors and all these things. So I think now this is the time to have the collaborations and have some good products of sensors, or we can say how we can help the automation of the any process or automation in the other area through this sensor, because these are very important. Though some of the sensors do not have any market, but this market will be developed soon, very soon, when we come up with some technologies. So then thanks to our team as well as participants and other members. Now I would like to hear from other panelists, because they are also expert in sensors, like RCI and this Miss Joran, because they are working on sensors since last so many years. Thank you.
Quickly, Bharat, because I may be leaving soon.
Yes.
I would request other panel, and I think Dr. Pakirisamy mentioned cost of regulatory process. I would ask him to spend some time, because not many people in this gathering may understand the regulatory process. This is fundamental. Without regulatory process, you cannot take even product to the market. That I can tell you. So forget about business plan, sort out the regulatory process first. And there's a cost involved in that.
Fine.
Yeah.
Professor Pakirisamy, kindly go ahead with your views, please.
Okay, thank you. So I was waiting for that. Okay, thank you. Yeah. So, and first of all, thank you for inviting me. And I think you understood CMAT is doing a wonderful job in sensors and materials, and I really appreciate that. And sensors is something. It is not one-man job. It is a one-person job. It is multidisciplinary. It's a transdisciplinary work. We need people from everyone to be part of it. So in order to be successful, first thing is a transdisciplinarity, which involves not only subject people as legal people also sometimes, because as a regulation is sometimes it could be a bottleneck in the whole development, right? This is the COVID time, the regulation was shortcut because emergency situations, right? Otherwise, you're not going to solve any issues. The regulation is a bottleneck all the time. So for sensors like establishment like yours, I think if you have some sort of a regulatory body helping you from the beginning, I think this will help the scientists what to look for when you really have something. Okay, this is something should be part of our team. That's what I always feel. Someone to advise us what is the best way to go about it, and that's a big job. So I will say interdisciplinarity should also include some policy people inside, not only pure technical people, non-technical people like policy decisions, the regulation bodies, and what to do and not. Okay, that's definitely it's a one to go. And also other thing is also I would, from the Indian perspective, I will say you don't need to look for FDA approval, for example. Okay, because FDA approval for America takes, of course, it's a big process, a lot of money involved, time. Okay, so you can have your own approval for India, right? It could be quicker, and you can have your own standard for India. That means we have a lot of people in India to serve first, than selling to outside of India. So that way, it will be quicker to the market when you have a regulation boards and regulation requirements developed for Indian context, not in the global context. I think that's a one step closer in that way, where we can be quicker, and definitely can be quicker. Another thing is also, I don't know, I'm a big promoter of innovation. I'm the fellow of National Academy of Inventors of USA. So I am a big promoter of innovations, and innovation in India, something to me has been sidelined for a long time. We have very creative minds, super minds, but they don't know what's innovation, what's the importance of innovating it, because we tend to throw ideas free, which is not a good idea to me. And somewhere, idea to be protected, whatever comes out of India should be protected. Don't go for US patents and stuff like that. You can have your own invention first too, so that it's something is there to start with. I think, and those things also should start on the side to protect all the technologies you develop, because that's equally important to me, because as more technologies are getting matured and more students are getting more excited about the opportunities, I see more students getting into making entrepreneurial platforms, and they want to make companies. When that comes, the sensor climate is quite different, and that will drive you sensors, the whole development in a different direction altogether. Okay, so I think it's not only technical sensitivity, technology development, also business, some sort of idea along with that. I think this is what happens in almost every country I see now. Every country I see that a lot of money is being pumped by the universities, by the government, on asking the good PhD student. Let's say you have a good PhD student comes out of, or any good researchers developing a beautiful product out there, some sort of encouragement to him. Okay, go ahead and try to do something, develop it to the people. Okay, I think that connecting, that is basically culmination of a good research for me, is that, right? One thing is good papers. I agree that very good papers you come out of it. And that's not the end of the research. The end of the research, especially sensors. Sensors has very relevance to the people, very relevance to the society. Okay, and the COVID, without sensors, we suffered for 2 years with COVID. It's just very obvious, right? We don't have that, and everything kills us. Even the technology was the regulation. This is everything finally pushed together. We are delayed. So sensor is a big thing, and we cannot develop sensing for fun. You have to do something to apply to the world, real world. So anything of that sort of matured way of thinking to take it to the public, I think that's to me I think interdisciplinarity to me, and to include even that, not only subject area of interdisciplinarity, even to take it to the public, up to the business development should be there. I think when that comes, I think institute like yours will be a big role to play in India. This is of course we are there, we can help, I can help. I have started up my own companies, and I worked with a few of my PhD students. They have their own companies. I help them to make companies, and sensing. There are many companies are being formed in Montreal now. So I'm into that area, promote innovation into really application to society. That's what I see. Somewhere you can incorporate the culture or the mindset into people. I think that will take the sense a long way, in my opinion, because that's my thing in this. Okay, that's my I've been pushing this everywhere, but this is something important for us. And other thing I wanted to interdisciplinarity, working with multiple area people. I think that is the key. It's not just project based. There should be a. I'm the training. I'm an aerospace engineer. I worked for DRDO to develop Kaveri engine. So I am the gas turbine guy. I moved something now completely different. So this is because I love to cross disciplines. Okay, I have no problem in crossing disciplines. So that kind of a interdisciplinarity has to be there for sensor, especially sensor needs that group of people. Okay, this is your materials, biology, photonics, everybody has to work together to come up with some sensor. So if we have platforms there to provide that. I think one good news I heard from IIC recently is that new hospital they're building, where hospitals, clinicians, and engineers are going to work together in the same building. That is outstanding. This is what I've been proposing for many, many years, and Stanford was doing it. In Stanford, when I visited, I saw a neurosurgeon is doing surgery assisted by a PhD postdoc of engineering student. He sees there what's the necessity of an equipment, what's the necessity of an instrument. It's not type, he's seeing it. So then you see engineer when see what's the problem is, then he comes up with a billion ideas. Ideas there. Only thing, the problem has to be seen right. That's a trick there, right? So when you give an opportunity to see the problem right there, he comes up with all kind of ideas. Then you see right away, you cross, like maybe I cross only 10 years, I could have time there. Just putting them there together, right? So this is what I would see cross-disciplinary to the core of working together as a one unit, not as independent researcher. So this is something I see. Then the sensors go it can go much better. This is just a small idea.
Thank you so much, Professor. Actually, just one comment before I request give it to Dr. Seema for continuing. Thank you so much, and I will come back to you all your comments. I want to say one small thing which is applicable to all others also. Of course, Professor Jha has visited us many times. You are most welcome whenever you are coming anywhere close to Cochin. We are very close to Cochin, and you are most welcome, sir.
I do come because I have a collaboration with the Mahatma Gandhi University with Thomas. Yeah. So we do something with Thomas.
Welcome, so sir. Kindly welcome. Welcome, sir. Dr. Seema, kindly go ahead.
I just want to add on to what Professor Pakiriswamy and Professor Animesh Jha has told regarding the regulations. So in India, we have the regulation is controlled by Drug Control General of India. Under that, we have a central drug standard control organizations for control. But for now, they have given the things for not only for drugs, but for medical devices also. So CMET has in fact developed a sensor-based wearable device for community screening of breast cancer and early detections and community screening. And this technology has been transferred to an MNC also. And they have submitted this for permissions. And after 2 years, they have got the NOC from the CDCSO on the medical device division itself. So in India, we have given the device, CMET has made the device, technology has been transferred for commercialization. And before commercialization, we have to get the permission of this Drug Controller General under CDCSO Medical Devices Division. And we have got, for at least for one of our product, we have successfully did all that things. So just to share that there is a mechanism now in India also, and many more regulations our government are bringing up for most of these medical devices. So from 2021 onwards, they have made mandatory for certain medical devices, all these many tests.
Well, congratulations. It's good news to hear. Thank you.
Thank you.
Thank you for sharing.
But still, we can take a cue from these experts and see how best the process can be expedited.
Okay.
Right.
I just want to, this is my last comment because I really have to go. I knew about this breast cancer device because Dr. Kale had explained and colleagues had explained. What I would say, one thing you must do if you embark on a new research and you have some early proof of concept that this might be a very good start, try to invite people into a workshop. Have a closed door workshop by invitation, include patients in that as well. So you definitely need support from doctors. And we do that here in Leeds. We have 4 big hospitals in Leeds University. 4 big hospitals. 50% of our student population, that 16,000 students are in the medical school, and remaining 16,000 in the engineering and other disciplines. So we invite people in a workshop, we discuss with patients, and things you will learn from patients is just invaluable. I must say that. And that really will help you in shaping. And I agree totally that you need to go to clinic to see surgery. I go to clinic to see orthopedic surgery and dental surgery, and I learn a great deal. I've been to the endoscopy room number of times and see the patient's pain. So we have a robotics program which reduces the endoscopy, whether you are doing esophageal endoscopy or whether you're doing colonoscopy, because you have to sedate the person, and regulation says you cannot sedate the patient for more than half an hour. So you have to stick to that. What can you do? So I think it's important to bear these points. So thank you very much. I better go. And very nice meeting you, Prof. from Concordia. Pakrisami, sir. Well done. Thank you.
Nice meeting you too. Nice meeting you too. Thank you.
Bye.
Thank you, Professor Jha.
Thank you. Bye.
Dr. Seema, continue, please.
Probably we can hear from Dr. Bose.
Yeah, we can hear from Dr. Bose.
Yeah, thank you. And good evening to all who are in India. And it's a very fortunate to suddenly get into this kind of panel discussion. And I really thank Dr. Kale for that. And I also appreciate the efforts made by organizers CMET Trishul. Basically, I come from ARCI, a DST autonomous lab, and mostly what we look at is the development of the technology and to take it to the level of industry. And this kind of convention is not very popular in our country, except few of our kind of labs, like including CSIR and CMET. But outside India, I agree many people and most of the professors, even who have already delivered the lectures, they go to the level of startup and opening an industry. So now the point here, as far as Indian context is concerned, I think we need to take so many things and learn so many things. And I agree with Professor Jha's very important idea of organizing such kind of instrumental workshops. And innovation is always an important part. We do have several type of sensors, maybe to the level of prototype in India. Every corner, every small university, every small lab must be doing that. But what I feel, they have to understand the terms like technology readiness level, because India needs a kind of atmosphere and a kind of facility, a kind of theme that we should be able to make these all sensors in our country. Now the things are not very straightforward. Even making one sensor itself is becoming so difficult when it has to cross from TRL 2 to 3 to 4 to 5 and reach TRL 10 is very, very difficult, because ultimately it goes to the industry. Our government is really keen on getting into or organizing some kind of a special structure for this. And with that perspective, our government, including what I would say DST, has launched a few missions, and where one idea was floated here itself that industry has to be there, and that kind of structure DST is actually following at present that whenever there is a call for proposal, not only the academia, but the industry is also has to join hand so that ultimately at the product level, at the commercialization level, what are the things which we as a basic researcher or a mid-scale researcher are trying to overlook or ignore many a times. So I think this whole structure, we are trying to align ourselves. It is a kind of a phase where a transition is going on, at least in our country. So Indians' efforts are there, but still there are very limited sensors. Those are being made here in our country. And I would always try to think on those lines that even at the university level also, we should seed these kind of ideas to bring out not only prototype, but a product. So even single thing is coming from one particular lab, we will have a chance to get into a lot of commercialization of the sensors by Make in India type of perspective. Now, I think one more last thing I would say, most of the, at least in this session, I was looking at health related, very important sensors. Those were presented. When in general, when we look at the societal type of needs, in India, we do have to also get into food related and agriculture related sensors. Now here I totally have to say that we have to make this with respect to Indian perspective, Indian conditions, because what happens, a sensor which is made outside India, it is made for some other climatic condition, let's say agriculture. So in Indian conditions, it may not work, and there is a lot of drift in its characteristics, and whole things either they fail or one has to waste a lot of money or spend a lot of money. So on these lines also, agricultural sensors are very important. And now when the whole world is driven by automation and IoT based or cyber physical based sensors, I think these all have to be thought in a very well organized manner, because India, lot many people, lot many ideas, realizing them to a level of first making a prototype becomes difficult due to lack of actually proper infrastructure. Like even if we talk about utter a word of MEMS, it's gone. We are very, means we don't have very easy access, or it's not very easy for everyone to do that. Maybe there are ways to do it within India, but when you go for miniaturization, the infrastructure becomes a very, very important part. What we can say that maybe there has to be some 4 or 5 facilities, centers, which will promote making these kind of miniaturized sensors. And that's it, because this kind of research industry will not directly come into and fund. And that is the whole tragedy. Even if we make a sensor, glucose sensor, electrochemical glucose sensor, it's becoming difficult. So I think I have also talked about the infrastructure related thing, and there has to be some maybe better organized policy to inherit few tens of centers. Those will actually promote this kind of miniaturization based sensor fabrication. So other than that, I think we have a lot of power, we have a lot of knowledge, and we have good ability to collaborate. And I'm sure most of the collaborators from India, Indians abroad they are always have been, we are always fortunate that they are ever ready to join hands and contribute to the Indian growth and technology. So I believe, yeah, in totality, all these points will be promote India as a sensor developing or sensor product making place, maybe in a few, let's say a decade or 1 decade or so, if the policies are promoting in this whole manner. So I think that is what at this moment I have to say. Thank you. Thank you, sir.
Thank you so much, Dr. Bose. Dr. Seema?
Yeah, now you can tell your views also.
Yeah, thank you. Respected panelists and friends, it was actually a real fiesta of a variety of sensors, components, devices that are, you can use one single word, really mind-blowing. Actually, I'm not quite sure that we as human really, in fact, we need to sit on the edge of our seat because everything was mind-blowing and superb talks. And we have to really use all our sensors, keep it active in order to assimilate the information that has been transferred for the past 3 days. I sincerely thank the organizers, including the convener, co-convener, Dr. Kumar, everyone who have made this wonderful fiesta of technical sessions. Coming back to the points, that take-home messages that has arisen out of these 3 days of knowledge exchange is that, one, I vividly remember that Dr. Karun Malhotra from Murata, Japan, he had already laid down the roadmap for India and what we need to do if we want to be self-sufficient in the area of. I think that's very, very important, and we need to concentrate how one can go from lab level to the production. He has given a very clear picture of how we need to do that. And if I remember right, WSC was kick-started with Mr. Bharani Iyengar, who said that if you want how to bridge the gap between whatever, as Dr. Bose has rightly said, many prototypes are available in India. Many universities are doing it. How to take it to the production, but how to bridge that gap, I think a lot of innovative ideas has been put forward. I think that will definitely help us. If we really look at the variety of topics that has been discussed over the past 3 years, including that of Professor Pakriswamy, what we understand is that a variety of materials, sensing mechanisms, detection methodologies, all these have been covered that are having impact in the area of health, electronics and IT, environmental, and other fields. If you look at the materials perspective, I think very clear that miniaturized devices with the thin films and newer materials like 2D materials and a variety of polymer-based nanocomposites that are flexible, wearable. So these kind of, if you really broadly classify the variety of materials that people have talked about, these are the things. And of course, a variety of detection mechanisms have also been, and the sensing mechanism have always been discussed already. So if there is no doubt that we could hear a lot about healthcare. For example, diagnosis at the cell level by Professor Arakya Swami, and the what do you call the electronic skin, and a variety of things has been done. And when it comes to the electronic and IT thing, we had right from paper-based electronics to all the way up to IoT sensors and miniaturized NEMS and NEMS based, everything was actually covered. And when it comes to environmental thing, we could see that people could talk about with clarity using, I think, similar technique to Professor Patrick. They used SPR technique to understand the water quality. That is very important. And a variety of things has been discussed about chemosensors, including TOD and other things. I think those are all very, very important. And the missing link, which Dr. Bose has already mentioned, is that India being an agriculture-based society, we need to definitely concentrate on agri-based sensors. There are a lot of cues and is feasible, and a variety of prototypes have been developed at different locations, and we need to locate them and ensure that it comes out as a product. I sincerely hope that Dr. Seema and their team, through their COE concepts, will pick up these basic work and see that it comes out as a product. Like that, the sensors for the livestock, the sensors for physically challenged, and geriatrics, because geriatric population is definitely the one that's going to grow in every part of the world. So those are something which are very, very important. And I think we should concentrate on all those aspects too. And the final part of what I have in mind to conclude is that just want to summarize what our respective panelists have said and what best we can answer for that. I think Professor Jha was very particular that one should come out with breast cancer, and Dr. Seema has already explained that we have come out with the most cheapest early detection for screening of breast cancer. And thanks to her, skills, she has come out with, we can do mass screening of the entire panchayat or the block or the district, and this has been done over the past 2 years across India, Northeast, Hyderabad, Maharashtra, Kerala, everything has been covered, and everywhere the users are very, very happy. They know that there is no pain. They're very comfortable. It is just whatever innerwear that they wear, it is similar to that. And that is one great success story. And she also explained the regulations, how that has been taken care by the company. Actually, the Murata India only took that from us. And the regulation has also been taken care. And so these are all the kind of, as Dr. Bose rightly said, we should have solutions for that will have to suit to Indian conditions, and that has been taken care. And Professor Pakirisamy was mentioning that policymakers should be there. I think we definitely have it, sir. In all our committees, our own ministry people are there, scientific experts are there. Plus, we have legal people also helping us to see how best we can go about. And now, the thing is that India is giving a lot of importance for innovation. That is one thing I would like to say, sir. The scenario has completely changed, and Skill India, stand up on your own leg, and Make in India, Atmanirbhar Bharat, all these slogans are definitely helping to see that innovative products are made in India and put to use in India. And as for the Professor Pakrisamy's comment that we should have interdisciplinary and connectivity, sir, I would like to humbly submit that the breast cancer technology that we developed is actually in association with the CDAC, which took care of the electronic part of the device, and in association with Malabar Cancer Center, and they only did the first field trial for us. Like that, the center that we are going to come up where the Dr. Seema, Dr. Radhika and all are involved on newly coming up. It is actually a national center. As our Dr. Bose was mentioning that there should be certain centers talking about certain aspects of it. So it's going to be on 2D and related materials, including graphene. So that we are doing in association with the Digital University. So we try to definitely see how best we can handhold and exchange our collaboration. And I would like to definitely love to see that our collaborations does not stop within the boundaries of our nation. If we can extend beyond, I'm sure that there our Indian diaspora will definitely help us. They definitely have a much bigger heart. And I mean, having born and brought up in this part for all those things, I look forward to that. With those humble words, I think I'll stop over here. Thank you so much for joining with us. Thank you.
Thank you. Thank you so much for inviting. It is my real pleasure to be part of this. And I've been working with many institutes like IIT, IISc, IIT Madras, IIT Roorkee, and many institutes. So definitely my pleasure to visit your lab sometime. Definitely. I think I see you're doing a wonderful job.
Most welcome.
And after hearing from you that in terms of interdisciplinarity and policy, I think I hear a lot about this innovation climate that has been created now. I hear a lot about that, and I'm very, very impressed with that actually, because I see there's so much potential out there. We need to provide the platform. I think that's essentially that's it, you know. And I am being myself from DRDO. I worked in DRDO for quite some time before I moved to Canada, so I know what it means in there. It's very well. So, thank you.
Thank you, sir. Thank you, Dr. Seema.
Yeah, thank you. So in fact, so whatever Professor Animesh Jha has told that, and also Professor Pakiraswamy has already told us that we should have whoever is using, we should get the feedback definitely from them only. So we had very close interactions with clinicians when we were doing the development of health related things. Similarly, we would have a very good interactions with associated industries. If we are going for some industrial products, then only we will understand that what they are really looking for. And when we have actually, if I say that in the first clinical trials, what we have conducted for this wearable device, in fact, we ourselves has went for all the clinical trials. We ourselves has discussed with the, when we are doing this first clinical trials and all, they have just diagnosed it only, because we want that kind of patients to be taken for this wearable device before they undergo any other test like biopsy and all. So it was under trauma, but women in India was very cooperative, and they have shared their experience because of their suggestions, valuable suggestions. Only we could modify our things. So that is also very important. I feel that women in India was very, very cooperative and helped us a lot in improving the products. And also similarly, even the director of this Malabar Cancer Center, Dr. Sadishan, was personally involved in this project. So then only we can get a success. So whatever they have told, I 100% agree to what they told. And similarly, whatever Dr. Bose has told, that is also very vital. So he has told that we have made in our, if you see that across our academic institutions or in our some of the laboratory, we have very good sensors, but at a lower TRL levels, maybe 1 to 3 or so. And we have to upgrade into a higher TRL level. We need altogether a different outlook and a different facilities. So I think that the ministry has been, our ministry is on Ministry of Electronics and IT, and they have really thought about that, and they have asked CMET. It is actually not from the proposal, not from the CMET side, but it's actually from the government side. So government has asked CMET to set up an Center of Excellence in IoT sensors. So they have given many IoT on the software side, on the hardware side, but they have given this particularly on IoT sensors, depending upon its understanding the importance of that sensors. Because IoT sensors, when you are thinking about the security, will come also a major part. So the indigenization is very important when we thought about this IoT sensors and all. So that's why, in fact, government has given a huge money. Both the government of India as well as government of Kerala has been involved in this to set up this Center of Excellence in IoT sensors. And we have conducted this seminar in association with COE on IoT sensors. We hope that we can have a collaboration with whoever. We are very open to have collaborations nationally as well as internationally to help our nation to become self-reliant in sensors. Kumar, if no more views is there, you can conclude this panel discussion.
Yeah, thank you, Professor Pakrisamy, Professor Animesh Jha, for spending your valuable time with us and coming on board and discussing the various possibilities with us. No doubt we are going to be in close association with you and other like-minded researchers in other institutions, because one of the ways in which we can make ourselves, India can make itself visible to the entire scientific community globally, is to cut down the speed. Because if we have to achieve that required speed to cut down on the translational, the time between the translational research taking into a commercial product, we need not only collaborative efforts with experts like you, but we would also like to have your intervention in probably advising us to see how best a student could be encouraged to initiate a startup, or how best our Indian laws could be tweaked to make things faster. So we will definitely be reaching out to you in the coming days, and we look forward to your active advice and participation. Thank you very much for being on board with us, and we certainly would love to be associated with everyone, each and every one of you in the coming days. Post-conference networking is going to be a very important aspect for the success, because we have the message now in front of us. How best these take-home messages are translated into practice. That is what I would urge our colleagues, including myself, to be engaged in the coming days, and see that things come out faster from our lab. Thank you so much. And I would like to, I was a little bit surprised to hear from Professor Bonex that when all of us were talking about miniaturized products, he was telling a very funny example in South Africa, where doctors are looking for bigger sized products, because they don't want to be searching for a product which is missing or lost by theft. So even if you have a small product, they put it in a big box and lock it, so that they don't have to look for it. It was on a what do you call a hilarious note, but on that hilarious note, we will conclude this session also. Thank you so much. We look forward to all of you through virtual interactions in the coming days. Thank you so much. And our invitation to each and every one of you to visit us is quite open and stands at all point of time. Thank you so much, and good night from all of us.
Thank you. Good night.
Thank you, sir. And thank you, Dr. Bors, for joining us. Thank you so much.
Thank you. Thank you very much, all of you.
Thank you.
So are we continuing, or we are winding
up? Yes, sir.
Up?
We can just have a concluding, because there is a concluding session. So we can just conclude our this 3-day conference on World Sensor Congress. So I think that Kumar sir, you can make a concluding remark also, sir.
I think each and every one of you have put in their best efforts, and I don't see any reason why we should not be happy about the outcome of this conference. Even though we have virtually met for 3 days, the amount of effort that has gone into the arrangements, I think I can only understand from the face of each and everyone. I can't see everyone any single person who is not tired or feeling sleepy at this moment. So that gives us a clear idea as to how much effort each and every one of you have taken to ensure that this has taken a real shape. But I would also like to caution everyone, including me, that we have to take a practical step to realize these take-home messages from these kind of, because many panel discussions take place and die with that. We have to take these suggestions and ensure that it is taken up in the right spirit, and we take a practical action plan on these things. Otherwise, we would perhaps miss the bus in this case also. India has missed the bus on many technologies in the previous years, but we should not miss the bus here. And kudos to each and every one of you. Marvelous job done by each and everyone. So perhaps we can meet later, tomorrow or day after, and have a formal meeting and acknowledge the contribution made by each and everyone. But I think students and youngsters in this lab, project students, research scholars, they have to get, they have to imbibe that research spirit. And because, you know, many universities abroad today, they have dispensed with the idea of having departments. There is no department in any major universities. You can't find chemistry department, physics department, electrical engineering departments. Today, universities are just recruiting people and then allowing the individuals to interact and form a team to address a specific problem. So if we can have that approach within CMET, let us begin with the well-known proverb, charity begins at home. Let us first write out at CMET Trichur. Let us not call ourselves as a ceramic person or a piezoelectric expert and so on and so forth. Let us try to reorient ourselves and try to form an ensemble to address a specific issue and then work towards achieving it. And that way only, I think we can promote more cross interdisciplinary research and then come out with specific products. If we can do that, tomorrow interaction with our sister labs at Hyderabad and Pune is just a matter of time. And within a few weeks, we can expand our tentacles to other organizations in India and outside India. So let us perhaps call it a day with this food for thought for all of us. Thank you. Thank you. All the best.
Thank you very much, sir. So, Regu sir, then we will conclude this WSE officially.
Yeah, actually, we should conclude, but I have only one point to make, if you don't mind. I'm sure that there are a lot of take-home messages, and Dr. Kumar has nicely summarized. And in case the audience, I think our own people only are there, our own scientists are there, and also Dr. Radhika, I have not heard her. So in case any one of you have something to share at this moment of time, I think we should give them an opportunity before we close. Is that fine?
Yes,
absolutely.
Yes. Karthik, you can make everybody
make
panelist
everyone
and open.
Yeah, just allow them to speak, please. Yeah, I think when he is doing that, I think we can start with one of you, whoever is there in that room, Dr. Radhika, Dr. Karthik, somebody can just start so that the process will keep moving.
Hello. Yes.
Yeah, madam, we can hear. Go ahead. Go ahead. Go ahead.
Okay. Just
no, your
I
audio.
have only a few words to say. Just after this. Hello.
Your audio is not okay. Your audio is not okay.
Hello.
Your audio is not okay. Your audio is not okay.
Actually, what is happening is Dr. Karthik has brought everybody inside. That's very good. But I think I request that all others kindly mute. Then only the person who is speaking will be able to hear clearly. Okay? Kindly mute your mics, then clarity will come. Thank you. Yeah, Dr. TR, go ahead.
Hello. Yeah, now it's okay. Hello.
Yeah, definitely better. Please go ahead.
Hello, am I audible?
Yeah, definitely better. Please go ahead.
Okay. No, just after the pandemic over, with the advancement of technology, a conference arranged in this platform, we could feel like it's not a virtual, it's a physical itself. And the talk speakers all were very fantastic. And it's, I can say, after the pandemic, it's like a refreshment for all of us. And I'm very thankful to be here. And as a listener also, thank you very much.
Any one of you, please go ahead. All others, kindly keep your mic muted, especially I think some Mr. Mohammed, Rashid, Dr. Stanley Jacob. If you're going to speak, kindly go ahead. Otherwise, kindly mute yourself. Dr. Roshini, yeah, those kind of people, kindly take care. Yeah, go ahead one by one. If anybody wants to say something, please go ahead.
Good evening to one and all. I am Ajay Pratap Singh from Delhi University. So, sir, it was a very good experience for me, or having such a nice views on the development in sensor and technology regarding that. So I wish it could be possible in physical mode, then it would be better. But as the situation is there, there is that we can't have this opportunity, so we have utilized much of that opportunity. Thanks to organizer for arranging such a very nice and what to say, a learning atmosphere or this thing. Thank you once again.
Anyone else, please unmute and speak. I think if no one else, Dr. Seema, I think we should wind it up. Thank you so much. Thanks for organizing, and conveners. As convener, you have done a very excellent job in ensuring that everything went off well. I not only thank you, I thank the entire CMET fraternity. I know that every scientist, every staff, every person has put all their effort. Thank you so much from my heart. Thank you so much.
So shall we call it a day?
Yes, sir.
Yes, sir. Thank you.
We'll quit.
Yes, sir. Thank
All the best.
Thank
Please
you.
follow up.
All of them, a big thank you.